So let's get started reviewing this multiple choice part of this exam. And let's be crazy and start in order with number one. Okay. Now, again, as we go through these questions, I would love for you to start paralleling what's happening in other tests that you've done. If you can start seeing some patterns, you can start seeing that some of these questions are very repeatable. So as I continue to do that in my other videos, no difference there. Starting with number one, I have a 0.5 mole sample of helium and a 0.5 mole sample of neon placed separately in two 10-liter rigid containers. They love to put gases in containers. Any case, there's a pinhole in this container, and they want to know which gas, helium or neon, will escape faster through the pinhole and why. So this is a classic rate of diffusion or rate of effusion type of question. Now, if you remember that you know that the rate of how fast a gas will expand into a room or mix into a room, or how fast the rate of a gas exiting a small pinhole is equal to the inverse of its molecular mass, or the square root of its molecular mass. So this would be the rate of gas 1, and this would be gas 2. So this is essentially a way to think about this. But we don't need the equation. I'm just showing you how I'm giving you Graham's law of effusion here to use. But all you know is the lighter gas, helium, if you look at your reference table, has an atomic mass of 4. And neon, again in your reference table, atomic mass of 10. The lighter gas, on average, will go faster, will be moving faster, and I love to draw these Boltzmann distribution graphs at the same temperature. This is neon, and we'll do number of molecules on the y-axis, and we'll do the speed on the x-axis. And if we have helium with the same volume of molecules, it'll be stretched out. Now the reason is because it's lighter, it's going to have some fraction of its total molecules moving faster. And if you don't like that, I always like to write, well, kinetic energy, one of the formulas you are responsible for knowing, 1/2 the mass velocity squared. If both gases are under the same temperature, they both have the same overall average kinetic energy, motion energy, the heavier one, the more mass, will have to have a lower velocity, or v there. So because the helium has a lighter gas, okay, its mass is lower, it's going to have a higher velocity. You could see it like this, or think of it that way. So the lighter gas goes faster. So helium will escape faster because helium atoms are moving at a higher average speed than neon, and that's the best answer for number one. And you've seen this before. You can't keep getting the same ones wrong. So hopefully that's something you'll pick apart and be able to identify moving forward. Number two. In number two, we've got the lattice energy of a salt related to its energy required to separate the ions. They're very nice of them to tell you what lattice energy is. Okay, and again, another question we see very often: which of the following pairs of ions is the energy that is required to separate them the largest? And this is based, again, on Coulomb's law. Coulomb's law is equal to the two different electrostatically opposed charges. Here's my charges of, let's say, the positive and negative, all over the radius between the distance between the ions squared. It's inverse square law. So as we've talked about before, larger the charges, larger the Coulomb's law, right? So as we go from +2 to -2, these Q's become greater, and therefore the electrostatic attraction between the positive and the negative increases. It makes it harder to remove those ions in the lattice, thus higher lattice energy. Now, the distance, well, as ions get smaller, the distance between them, okay, will get closer, okay? Or I like to think of in terms of, easy for me to say, is that if the ion gets smaller, its charge density increases. So look what they say. Assume that the distance between the ions is equal to the sum of the ionic radii. So let's assume that the positive and the negative are right up against each other, and as these ions get smaller, okay, they're closer together. So as they get closer, the electrostatic attractions, of course, increase. So in this case, I'm looking at um, I'm looking at my A and B here, and I'm going to eliminate those choices because to get the greatest coulombic attraction or electrostatic attraction between the ions, which would again make it harder to remove, I want higher charges. So A and B have the lowest charges, plus and a negative for Q. So those lower charges would lead to a lower attractive force and therefore easier and lower energy and lattice energy to remove the ions. So I'm basically getting rid of A and B. Now it's between C and D. And these both have the same Q. They both have the same charge. So the next piece of this is, what about the radius of the ions? I'm looking for the smallest. Now we both have oxygen here. So now this question comes down to magnesium versus calcium. And I look at my reference table, I can see that both of these are alkaline earth metals. They're both in group 2. That's the second column. And you'll see beryllium, okay, above magnesium, which is above calcium. And what we know is that as we go down the column, the radii of the atoms get bigger. Now, I say atoms here, and you say, Mr. Grotsky, these guys are ions. So how do I know the difference? Well, all of these guys become +2. They're all going to lose 2 electrons to basically be as stable as their noble gas counterpart on the other side of the periodic table. So they're going to lose their 2 valence to become stable, so they have a filled octet or a filled shell, whatever you like to use. But since since they're all losing 2 electrons, okay, they're all getting smaller. As you lose electrons, the protons outnumber, so they're all getting smaller. And they're all getting smaller, we can assume, about the same amount if they all have the same electrons lost. So if that's the case, they're all getting smaller by the same amount. It's all about how big they were before they lost electrons. And as we said, as you go down a group, the radii of the atoms get bigger. Okay, as if you learn quantum numbers, n indexes size. But if you like the fact that as you go down, you have extra what? Shells of electrons. That's also another way to think about it. Calcium being in the 4th energy level, okay, has 4 shells of electrons. And of course it loses 1, so its remaining is 3. Magnesium, of course, is in the 3rd energy level. It loses its 3rd to become Mg+2, so now it has 2 remaining. Beryllium has 1 remaining. Bottom line is calcium's bigger because it's got more electron principal energy levels left. So because it is bigger, the calcium, okay, it's got a bigger radius than the magnesium. What it's going to do, a bigger denominator, is going to lower the coulombic attractions. So you can see that D will not be the answer. Magnesium will be the smaller ion because it starts out smaller. Therefore, it'll have a smaller distance so that its high charges can have more effect. And if you don't like any of that, okay, again, Coulomb's law is the Q of the opposing charges over the radius. And if we have again, smaller radius because it's found higher on the table, a smaller denominator makes a larger, okay, value for Coulomb's law overall, and that'll make a higher lattice energy. That's why number 2 is choice C. Number 3. So in number 3, we're talking about and looking at some data from a mass spectrometer. And a mass spectrometer is nothing more than a machine or a device that takes an atom, pulls off an electron, the resulting ion is basically attracted by a positive ion, I should say, a cation, is attracted by a negative field and goes through an opening, and then essentially is pushed through, okay, or again, attracted, basically accelerated because of this negative charge through this negative field. And then you have opposing magnetic fields. And essentially, a moving charged object will create a negative, positive, well, a north or a south pole kind of a field, magnetic field. And then we have this magnetic field pushing on it in a certain direction. So it kind of bends it, and eventually it hits a detector. Now, the heavier that the ion is, the less it's affected by that magnetic field, and the lighter the lighter that particle or that positive ion is, okay, the more it's bent toward. Now, of course, these things are calibrated first and they're synced so that there's motion. But basically, what we can do is we can measure the distance between these hits on the detector, and what we get is a relative scale of mass. If this was hydrogen 1, hydrogen 2, and hydrogen 3, okay, these hits on the screen relative to each other by distance is how we determine the difference in masses. So this could be hydrogen 2, the black here would be hydrogen 1, and the blue would be the hydrogen 3. I don't know if I drew this very well, but these distances are equidistant from each other. So if it hit here on the detector, we can measure the mass, or the distance, I should say, the distance between these hits, and we can measure also the relative amounts of those hits. That's how we get these distances. In any case, so what we get from a mass spectrometer is something about a factor of its mass, and the same element has different mass forms. Okay, for instance, carbon-12 has a very famous isotope, carbon-14. It also has a bunch of other ones, okay, that are existing or can be made. And the point is that carbon, like all other atoms, has many forms of the same element, same number of protons, different number of neutrons. So a mass spectrometer is measuring the different masses of a same element or a mixture of elements. It's looking for isotopes. So anytime you see this question, all right, we're looking for isotopes, it's about the masses of the neutrons. So I can get rid of choice A and B because they're talking about electrons. This is about how heavy the atoms are, and the electrons are 2,000 times about lighter than a neutron or a proton. So it's about the neutrons or the mass of the element. It's about the isotopes. So choices C and D are about isotopes, and you can always do that when it comes to a mass spectrometer. Now, the question says, based on the spectrum, which of the following can be concluded about element X? All right, now they're saying the atomic mass is 90, or the atomic mass is between 90 and 92. And again, when we look up the masses on our periodic table, for instance, an example, hydrogen, okay, has an atomic mass of 1.008. Yet we know that we could get all three of these, different forms of the same type of element called isotopes, different number of neutrons with the same proton number. Hydrogen having 0 neutrons, this having 1 neutron, this having 2 neutrons. And this is the radioactive form called tritium. But the bottom line here is that the overall mass of hydrogen is 1.008 because they average them together, and because the most abundant isotope, and there usually is one of its isotopes for an element, is usually the most abundant in nature. Just like for element X, we can see 90 is the most abundant. That would mean that this 90 hit the detector the most often here than the others. And that would mean that the atomic mass, when you average the relative amounts and their abundances using the percentages in nature, that element X is going to have a average isotopic mass closer to 90 than the rest of these. Okay, so just like for hydrogen, it's closer to 1 than the others, but this still doesn't help us for the question. Well, it kind of, because they said atomic mass is 90. It can't be 90 because we have other what? Isotopes that are heavier. So it has to be heavier than 90. So that's why we can get rid of C, and D is the answer. It's not going to be 90. A mass spec is not going to tell us exactly the most abundant isotope, and therefore the mass is 90. What we get from atomic masses using the mass spectrometer is we get an average. We would average these using their abundances, using their percentages, and that's a weighted mass problem, okay? So the atomic mass is between 90 and 92. Why above? Well, because the other one's above. But why between 90 and 92? Because if you notice, most of the hits on the mass spectrometer are in the region of 90 to 92. So that means the mass, the average mass, would be somewhere in there. That's why D is the answer. Now I'm going to show you something called the weighted mass problem, and I'm just going to show you to the right in a second how I could calculate this, if in fact you saw this in part 2. Okay, so what I have here is the weighted mass problem, and all I did was I essentially just guesstimated what these percentages would be. Okay, so I guessed at 53% from the mass spectrometer of all the isotopes of element X, okay, of element X is isotope 90, okay, the mass of 90. And then I did 10% for 91, so at 91 I got about 10%, 18% for 92, 18 for 94, and I just guessed 2% for 96. These are all estimate values based on just trying to read the height of these columns here. And all I found was from those percentages, or I made them into decimals, and I times them by 53% of 90 is 47, 10% of 91 is 90, so I just basically found the percent of all these atomic masses that I got, and then I add them together, and that's how I get a weighted mass. Now, of course, the answer says between 90 and 92. My estimates got 92.2, but close enough. So they could, at some point, ask you to do a weighted mass problem, and that's what this is, and we did this in Regents chemistry or in other chemistry courses. Again, all I did was read the percentages, and I took that percentage of that exact isotope, and then I added them together, and I call it a weighted average problem. Okay, number 4. In number 4, which of the following diagrams best depicts an alloy of nickel and boron? So they love to talk about alloys, and we have substitutional alloys and interstitial alloys. Substitutional alloys is when you're basically placing another metal in place of the other metal that will fit nicely in the crystal because their atomic radii is approximately the same. This would be an interstitial alloy where the smaller atom would fit in between, and this would change its properties in terms of hardness because it's harder for this to now move down if you would try to strike it and cleave it, because this little ion is kind of prevents it, so to speak. This right here is not a crystalline pattern of an alloy or metal. These are just molecules that are probably in some kind of crystalline pattern based on their polarity, so forth. So this is not a metallic substance. This is a more covalent substance, not even a network. And of course, as we go down, choice D is an ionic substance. So I can cross out the ionic substance, which is positive, negative. I'm dealing with metals, and the basically the crystalline structure of a metal is due to the nuclei. So it's got positives, yes, but no negatives there. There's no ions here. So the question is nickel and boron approximately the same size? Well, I know nickel is a metal, and boron is that metalloid that's moving closer to the upper right-hand corner of the periodic table. So if we go to the periodic table, let's just see if there's some similarities in their radii. So looking at your periodic table of the elements, we have our metals here. Okay, you can see most of your metals of here and our metals that we're dealing with. And then we've got boron. Okay, now boron is going to be in a second, okay, row, and it's moving closer to the fluorine, or the area where they get really small. So I'm going to make the guesstimation that boron, being in the second energy level, not the fourth, has less what? Shells of electrons, is going to be much smaller. Okay, yes, it's a metalloid, okay, but I would say it's going to be much smaller estimation-wise for the fact that it's over to the right a little bit of the metals we're talking about, okay, and it's in the second principal energy level, so only has two shells of electrons, or electrons are occupied in two energy levels, which is going to be much smaller than occupying energy levels of the fourth and the three. So I'm going to say that the two differences between the metal and the metalloid here are going to be big. So the nickel is going to be the big one, and the boron has to be much smaller because of only 2 occupied Prince Muncher levels, where the nickel will have the 4. So I'm going to say we're going to have an interstitial type of alloy, which is going to make it harder. A is the best choice because of those differences in atomic radii. Number 5. Which of the following is the strongest type of interaction that occurs between atoms within the circled areas? Okay, so we're looking at some nitrogenous bases here. And we see that when you have fluorine, oxygen, and or nitrogen, these are electronegative enough and small enough to pull these pair of electrons between them, NOF, doesn't matter, between the hydrogen. So what happens is these guys have such a great attraction for electrons and are small enough, can pull and drift these electrons away from the H to the N to the O to the F bond to expose what's left. And what's left in hydrogen, if it loses its valence electron, so to speak, it's not lost, it's not an ion, but it's as close as it can get. What you're exposing is what's left is that proton. So if you've got nitrogen pulling that pair close, really all you have left is a proton. And we call that electron deficient hydrogen. That is what causes the H bonding. So this is H bonding between the electron deficient H and the O. This is really a proton. It really will attract the negative end of this oxygen. And also, remember, this is very electronegative, so it's electron rich as well, not so much as oxygen, but part of the 3. So this electron deficient H will also attract, and that's why we're talking about hydrogen bonds. But if I had a carbon hooked up with an H here, that's not electron deficient. Anything else bonded with anything other than a fluorine, oxygen, or nitrogen would not be electron deficient. It would not have the attraction necessary to make this hydrogen bond. Now, it says bond, but understand it's an attractive force. It's not truly a bond between atoms. It's an attraction between molecules. In the case of DNA, it's what keeps DNA together. Okay, so that number 5 is C. Number 6. So in number 6, we're talking about a hot iron ball dropped in water. Scenarios like this, these type of thermo questions, I always like to tell my students to draw what's going on. So we've got an iron ball that's hot, okay? And it's dropped in a 200 gram sample of water. So just going to write that 200 gram sample of water, which is initially at 50. It's pretty warm to begin with. And what they're telling us is 8.4 kilojoules of heat is being released from the block. So just by saying that, if 8.4 kilojoules of heat is transferred from the ball to the water, I know the water's temperature is going to increase. I know temperature initial is at 50 degrees Celsius. They want to know what the final temperature is. Well, we've seen this in other courses, so this is no big deal. So we're going to use Q equal MC change in T. They're giving us the specific heat of water. So I know we don't have a calculator here, but the math is simple enough to do. Now you have to understand your specific heat is given to you in 4.2 kilojoules, all right? 4.2 joules per gram per degree Celsius, excuse me. So we have to make sure that we're in the same units. So I'm going to make sure that the heat transferred is in joules, and quickly 8.4 kilojoules, all right, is 8,400 joules. We should be able to handle that conversion without me showing you at this point of your AP chemistry career. Now, mass of the water is a 200 gram sample, so that's 200 grams. It's always about the water. Okay, so remember, if you want to think about this, the energy transferred to the water is equal to the mass of the water, specific heat of the water, change in temperature of water. These Q's are always about the same thing. If I was to really set this up, I would say Q of the what? Ball is equal to the Q of the water. Okay, and why do I do that? Because the energy released equals the energy gained. Now, in truth, if we're doing real thermodynamics, we put a negative in there, but they're just talking about the temperature change of water, so we're going to keep things simple. Okay, so my specific heat is 4.2, and again, it's important to note the units only because that reminded me this kilojoules had to be in joules. If you went too fast and didn't consider the units, you would have gotten this wrong. And of course, some people are going to solve temperature final minus temperature initial, and you could do all of that. Okay, I like to think, even in AP land, it's easy to solve for the change in temperature first. Okay, to keep your math simple. So in any case, my gosh, I don't have a calculator. How can I do this? Well, 2 times 4.2, I'm going to solve for this, right? So all of this is going to go on the denominator. So this becomes 8,400 joules over what? Well, what's 200? What's 2 times 4.2? Well, 8.4, and add 2 zeros, 8,400. You should be able to do that, honestly. Okay, and if you want to notice the grams go bye-bye, and this is actually joules over degrees Celsius, and as you can see, if you want to cancel, we get degrees Celsius out of this. But back to the math, 8,400, okay, and I see I made an error. 8,400, this is 840, okay, right? 2 times 4.2 is 8.4, and then I add 2 zeros, 840. So 8,400 divided by 840, hopefully you can see that increases by 10. Okay, the math is simple enough for you guys to do. It's not about having a calculator. But what did we solve for? We solved for the temperature change. Okay, and because we know that heat was released from the bowl into the water, the temperature went up 10 degrees. The initial temperature was 50, so I'm going to add that to my initial temperature, and I get a 60 Celsius change. Not a big deal, okay? Not a big deal whatsoever. Very easy problem. One that I've seen in part 2s in the new format. So number 6 is C. Moving forward, number 7. So in number 7, they give you these containers, okay? Each of these is filled with N2 gas, and it's sealed, okay? And 4 of the 5 also contain these solid compounds, all the same moles, okay? And the volume of the volume that these take up don't do much, or it's an insignificant amount of space. Yes, 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 and the pressure, okay? And they're all at the same temperature. So number 7, after all this information, number 7 says at 127 degrees Celsius, which is the same temperature, I'm noting that, the pressure in vessel 1 is found to be higher than vessel 2. So number 1 is higher in pressure than vessel 2. Okay, so these are being compared. So in my mind, if there's a higher pressure, it's because, well, something about this solid at that temperature decomposed into gas particles that increased the number of gas particles that, of course, increased the number of collisions on the container wall, which is what pressure is, a force over the area. So which of the following reactions is increasing the number of gases? Well, looking carefully at my choices, I have carbonates involved. Hey, anytime I've got carbonates, I know they love to dissociate into CO2. If you look carefully, party people, there's only one choice that breaks apart into CO2. So this question isn't about, hey, do you know exact chemical formulas? It's not about that. You should be able to understand that if you've got a carbonate, okay, it loves to give off CO2 because the CO2 is a stabler form than the carbonate is, whether we add an acid or we add heat. And if you didn't know any of that, you should realize that we don't give off CO3, okay? And if you notice your other choices, A doesn't make a gas, does it? B doesn't make a gas. So look at, the only one that makes a gas was choice D. So it really should have came down between C and D in terms of which of the two is adding more gas molecules, all right? But the only one that makes sense, you should know enough about chemistry to know that carbonates become CO2, all right? And that's why C is the answer. It's the only one that increases gas molecules. 2 choices did, but the C2H2 makes no sense. Again, it's not about knowing reactions, it's a generality, and the generality here is that carbonates make CO2. And that's the one that increased it. So number 7 was C for that reason. Number 8. Okay, number 8, in one of the samples of the boxes, because this is basically a question or a group of questions based on that setup that we have here. Okay, so this setup have here, one of the boxes has iodine. And at that temperature, all the iodine vaporized, or we should say sublimed, into this box. Okay, So that's what's happening there. All right. So at 127, the entire sample is observed to have vaporized. How does the mass of vessel 5 at 127 compare to its mass at 27? So again, going back to the problem, these guys were at 27 degrees Celsius, including the question we just did, and by increasing it to 127, that heat made this guy give off CO2, and that heat made the solid iodine vaporize or sublime. But the question is, how was the mass before this solid sublime and the gas in here? How do they compare? Well, we didn't add any more atoms. It didn't come out of nowhere. Conservation of mass states that the mass before the reaction is the same mass after. There's no pinhole for the gases to leave. So the mass is the same since the number of each type of atom in the vessel is constant. We had iodine as a solid, and then we had the gas that was already in the container, and none of that changed. The number of atoms never changed. Yes, they changed from a solid to a gas, and the gas was moving faster, but again, conservation of mass. So that should have been an easy question that we should have gotten. So the mass of them, of course, is the same because we didn't lose any atoms, we didn't gain any atoms, we changed their phase, but the number in each type was constant, so number 8 is B. Number 9. In number 9, the gas particles in vessel 3 at 27 are represented in the diagram above. And notice they're not all going the same speed. I keep talking about Boltzmann distribution graphs. There's going to be a range of speed, okay, for a number of molecules at a certain temperature. But now that's at 27. Now if I increase that temperature to 127, what happens? And you should be aware, the number of molecules doesn't change, hence number 8. So this is going to actually flatten out. Okay, so if I was to draw this appropriately, this would be the same volume but flatten out. Now you have what? More molecules that are faster. It doesn't mean that everyone's faster. Okay, so if I look at my choices, okay, what I could get rid of is number D because 1, 2, 3, 4, 5, 6, 7, 8. That's 8 molecules. We didn't increase the number of molecules. All we did was make them go faster. Notice we started with 4 in my drawing, so I can get rid of something as silly as D. Now, also I'm going to get rid of is letter C because we're showing some chemical changes here, okay? And there's no indication of any chemical changes. This is breaking stuff apart, okay? So I'm going to get rid of C. And B, okay, all I'm doing in B is, if you notice, that's kind of close to what we have already. A is the best representation. It looks like these arrows in A are a bit longer on average than the arrows, okay, initially. I mean, say, Mr. Gronsky, what about this particle? It's going really, really slow, but these arrows are big enough to overcome that. Remember, it's a range of speeds, not all going the same speed. So it looks like to me, B, the collective motion or the collective sum of all these resultant arrows are going to be smaller than the sum of all the arrows, okay, here. And it looks like on average, and it's all about the average, okay, A is going to have more kinetic energy, a higher temperature, higher kinetic energy, but that kinetic energy is an average. So if I was to take this 1, and if I made this arrow 1 and I measured this to be an 8, and this was a 6, and this was a 5, and I averaged them together, it's going to be a higher average than this one, and a higher average probably of B. So A is the best answer for number 9. Number 10. Number 10. Oops. Okay, number 10. An acetate buffer solution is prepared. That's nice. They told you that. They shouldn't have to tell you that. Because if I have 50 milliliters of acetic acid and 50 milliliters, equal amounts of 0.2, the acetic acid is 0.2 molar, and they're giving you sodium acetate, which you should know dissociates. The sodium is always soluble because the sodium ions are always spectating. So that's going to make C2H3O2 negative. And because we have what? We have equal volumes and equal concentrations of both, okay, you're going to have the same number of moles. Liters times the molarity gives you the moles. You have equal moles. So what we have is the perfect buffer or the max buffer position, okay? So equal amounts of conjugate acid, conjugate base. They were adding the salt, of the conjugate acid, which is one way. The other way we talk about is what? Titrating halfway to make a buffer. All right, so we've got a 5 millisample of base is being added to the buffer. Not telling you it's a base, but we can clearly see that strong base. So we have a little bit of base is being added. Which of the following is the correct pairing of the acetate species? That means either the conjugate acid or the conjugate base is in higher quantities, in greater concentration. And what will be the relative pH if I add a little bit of the base? Well, we should all know, okay, that when we titrate, okay, with a weak acid, or if we create a buffer region, what we're dealing with is something like this. Now, what I've been teaching everybody is that when you have equal amounts of your conjugate acid and conjugate base, we've got something special, and that special is a max buffering position, and we know the pH equals the pKa. Why? Because the pH equals the pKa plus the log of the conjugate base concentration over the acid. And when they're equal amounts, this goes to log of 1, which is 0. And that's what you're left with. So we know the pH is equal to the pKa. They tell me the pKa is 4.7. So 4.7 is this position. Now we're going to drop some base onto this buffer, and the acid part of the what? Buffer right here is going to neutralize it, okay? But essentially it's going to push the pH a little bit higher. Why? Because we took out some of the acid. Remember, now it's the log. Now this comes back, the log of the what? A minus. Okay, I'll do the A minus, that's the conjugate base, over the conjugate acid. There's going to be a lot more conjugate base, okay, than conjugate acid because we ate up some of the what? Acid, and as you do so, you make more conjugate base. So this now is going to be greater than 1, and the log of something greater than 1 is going to be some value that's positive. And you're going to add that to your pKa, and that's why it increases somewhat. So this line is going to go up a little bit. So you're going to be above 4.7. That's why we do above 4.7 is our answer. Because for two reasons. We took away the conjugate acid because the what? The base reacted with the acid, and therefore you lowered the conjugate acid. All right. And as you do what? And this is important, even though you may see it already. As the HC2H3, the acetic acid, is forced to give up its H to the strong base, you make what? You make more conjugate base. So we're lowering the amount of the acid by dropping the base, but we're also increasing the amount of this at the same time because we're forcing the reaction to go forward. And that makes this top number in the Henderson-Hasselbalch equation bigger. And now it's not a zero factor. This becomes some significant number greater than 1. And we add that to the pKa so it gets bigger. The question is, okay, which choice is it, B or C? Well, who's in greater concentration? We're lowering the acid, increasing this. Clearly, the conjugate base is in greater concentration, and clearly it's greater than 4.7 because we're eating up the acid. So choice D for number 10. Number 11. So what we have here is the molecular formula, okay, and the molecular mass, the molar mass, mass per 1 mole of the compound, okay? And what the question states is, based on the information, which compound has a higher boiling point? And we know that higher boiling points result by molecules attracting themselves stronger. They're not bonds, they're attractive forces. And the attractive forces, trying to draw dots here, between the molecules, my little circles here, if they're stronger, it's harder for these guys to separate and leave the liquid and go to the gas phase. So the question is, Who has a higher boiling point? Well, the ones with the stronger attractive forces. So now that we have to identify who has stronger attractive forces, and a great way to talk about it is intermolecular forces. These are forces between atoms. They're not bonds. And so often I see so many chemistry students talk about breaking bonds. These guys right here are attractive forces. We have to break them, okay? These attractive forces, not bonds. The bonds are in between the atoms in the molecule. Now, how do I know which one has the stronger intermolecular forces? Well, if I look at these formulas, these are hydrocarbons. And hydrocarbons, because of their nature of the carbon to hydrogen bond, which is essentially nonpolar, make nonpolar molecules no matter what their shapes are. And if things are essentially nonpolar, they have these London dispersion forces, which is about the cloud of electrons they have and how well they can be deformed. And deforming this cloud is called polarizability. So the bottom line is the shape is important. Since these are both N-chained hydrocarbons, meaning they are straight-chained, we have no reason to believe otherwise because they're so small, okay, you can say that the longer chain here is more polarizable for having a longer carbon chain, but you can also say better that they just have more electrons. Having more electrons in your carbon cloud, okay, makes it easier for this cloud to deform. When I say deform, if you have something that's positive here, these electrons can deform its shape and move more to this area, creating a negative area and another positive area. So as these electron clouds kind of deform a little bit, that's how they make these momentary polar dipoles. They're momentary because as soon as the molecules move away, they don't attract each other. So the attractive forces here, London dispersion forces, are dependent upon the polarizability. It's a word you need to start getting down. We've been seeing this popping up in part 2s and now in part 1s. So having more electrons in C4H10, okay, is the reason for a greater polarizability, meaning having more electrons, these electrons are able to create a greater positive or greater negative area because there's more to move, more to deform, okay? And that's why B is the best answer, okay? You can't say polar because they're not really polar. They make momentary polar charges. They don't make dipole. They don't have permanent dipoles, okay? And C2H6 is smaller, and they can get closer, and that would represent stronger dispersion forces. Well, being closer is a factor, but it doesn't have nearly the number of electrons that C4H10 has. So this is the best answer. Polarizability is the number one reason for the strength of the London dispersion forces. So 11 is B. Okay, number 12 is listing the ionization energies. That's the energy it takes to pull and yank an electron away from an atom or an ion. This is the first ionization energy. This is where I took an atom and removed its electron. This is the second. Now it's a positively charged ion called a cation, and it's going to be harder to remove because now it's +1 because I removed it. So the second ionization energy is always going to be higher. And thus the third ionization energy, it's going to be even higher because now I'm trying to pull away something that's +2 because in the first and second ionization energies, I yanked 2 electrons away. So this thing is +2. Harder for electrons to remove that the nucleus, effective nuclear charge, is increasing, okay? Now, interesting enough, you can see these are increasing from the first to second to a third. Okay, it's increasing, but all of a sudden there's a huge, huge, significant leap between the third and the fourth. Yes, 800 to 2000 is big. Yes, 2000 to 3000 is big, but this is a huge leap. And if we're talking about a huge leap in ionization energies, the reasoning behind that is because we're removing electrons that have even increased stability. See, we use ionization energy to measure the stability of electrons. What do you mean by stability? Stability is how low energy that they have. Things that are stable have low energy because they'll stay in that position until you give them energy. So you need to recognize this huge leap from the third to the fourth represents a huge difference in stability. Why was I able to pull these electrons away relatively easily, even if they're positive 1 or positive 3, when the fourth and fifth was a huge difference? Well, because there's a huge difference in the stability, and these electrons here that I'm trying to pull beyond the third, okay, must be core electrons. Electrons held closer to the nucleus, electrons in stable electron configurations. And these electrons that are easy must have been the valence electrons, the electrons that were exposed out of the core that are not as stable. So in number 12, the first 5 ionization energies of a second period element are listed in table above. Which of the following correctly identifies the element? So we're looking for something with 3 valence electrons. So between boron and nitrogen are my choices. So boron right here has 1s2, 2s2, 2p1. It's got 3 valence electrons. It likes to lose 1, 2, and 3, and boron likes to become plus 3, just like aluminum. All these elements have 3 valence electrons. Carbon has 4. This has 5. 1s2, 2s2, 2p3. So this has 1, 2, 3, 4, 5 electrons that are not in a what? Filled Prince energy level. Boron has 1, 2, 3 electrons that are not in a filled energy level. And then here I have the what? The core electrons. Notice there was 5 ionization energies that got increasingly higher once I started pulling them from the filled energy level. So boron is 3 valence. Nitrogen has 5 that are exposed, so it makes sense that boron is the answer there. So if I look at my periodic table, my boron and nitrogen are my choices. And if I look at nitrogen, nitrogen is 1s2, 2s2, 2p3. It doesn't fill the second principal energy level. It's got 1, 2, 3, 4, 5 electrons beyond the filled first. So in essence, it should have 5 ionization energies that steadily go up, and then that 6th ionization should jump through the roof. So nitrogen has 5 valence, and that's why it's not the answer. Boron is 1s2, 2s2, 2p1. It's got 3 valence electrons. In fact, it likes to lose all 3 to become as stable as helium and become a plus 3 like aluminum and gallium. This entire row likes to become plus 3 because of that reason. But boron has 3 electrons that are outside a core. You notice it was the first ionization energy, the second and the third that increased, and then the fourth is it really jumped through the roof. Why? Because I was removing that 1s2 electron. All right, so that's why boron is the answer. It's the only one there that has 3 valence. So the answer is boron because it has 3 valence electrons, choice B. Number 13. Number 13 states the exothermic dissolution. We've seen this pop up before, and it just means that something is dissolving in water. Okay, so you'll see that word pop up again. Is represented by the equation above. And we've seen in part 2 in our practices where they've asked you to write the dissolution of different compounds. And here in part 2, part 1 in this test, they're giving you the example. So whatever we're working on in multiple choice, hope you can start to see that we're seeing the same thing in part 2. All right, so this is exothermic. That would mean that I'm giving off heat, and I'm going to put the heat on the product side. Okay. Now the KSP is very small, which means it barely dissolves. Okay, which of the following changes will increase solubility? Now, what in the world is solubility? Solubility is the measure of how well substance can break apart into its ions in the presence of water. So if you're going to increase the solubility, we're going to basically make this reaction become more spontaneous in the forward direction, or shift to the forward. So this is really a Le Chatelier's principle. So which of the following will do that? Well, if I decrease the pH, that means we're going to get more acidic, and that means we're going to probably add more H pluses or H3O pluses. Now, if we do that, H pluses will react with the hydroxides to make water. And if I use my chart, if I have to, stress response, if I was to lower the hydroxide, the reaction is going to look to make more hydroxide. So if you notice, by adding H pluses, which in fact lower, that's the stress I apply, the reaction is going to shift to make more hydroxide. So that reaction would shift forward. That means more solid would dissolve, and that increases the solubility, and that's why A is the answer to Le Chatelier's problems. Okay, let's look. Increasing the pH would not work for the same reasons I just explained. How about adding ammonia to the solution? Well, there's no ammonia here, so you might say, well, there's no difference, but you should know that ammonia is a weak base. You really should. And if you put it in water, what's it going to do is it's going to yank an H away to make the ammonium ion. Okay, and that's not a big deal, but it's the what? The resulting hydroxide you just made. So what that would do is that would increase the hydroxide concentration. That would be increasing the hydroxide, and the response by the reaction would to always lower it, and it would shift the opposite, so that wouldn't have any effect. You should be aware of this reaction. Now, adding magnesium nitrate to the solution has absolutely no effect because it's a solid. We measure the spontaneity by Q versus K. You know, is it bigger or less than K? And Q and K are measured by what? Concentrations of the products over the concentrations of the reactants. A solid and liquids do not apply, so this would have no effect whatsoever. It's really important in this case to go over the wrong answers, choices, as well as the right. 13 is A, number 14. Number 14, the heating curve for a sample of pure ethanol is provided above. The temperature was recorded as 50 grams of the sample was heated at a constant rate. Which of the following explains why the slope of segment T is greater than R? So the slope is kind of flatter for R and more steep for T. So why is it higher? Okay, well, this is temperature. So we're watching, now you should understand this. This is the solid phase, this is the liquid phase, and this is the gas phase right here. So why is the gas increasing its slope or its temperature faster than the solid, than the liquid? Why? Well, what do we know about temperature change? It's based upon specific heat, right? We use our Q formula, Q equals MC change in T. Okay, well, if the same amount of energy is being added at a constant rate, so this is staying constant, and we know the mass of our sample is staying constant because it's the same substance, then it's about these two scenarios here. Gases, if their temperature, okay, is increasing, then it must mean the specific heat is lower for the gas, right? If you have a lower specific heat, that means you can change your temperature more for the same energy. We have seen this over and over and over again, even in part 2, the free response section. These are things you have to start getting down. If you solve for C from this equation, what do you get? You get the Q, the joules, over the mass change in temperature. Okay, so you can see that a higher temperature change results from a lower specific heat. What is specific heat? The amount of heat it takes to raise 1 gram of a sample 1 degree Celsius. If it's raising higher here, if it's higher temperature, it must mean that the specific heat is lower. So the specific heat capacity of the gas ethanol is less than the liquid and or the solid. Okay? And of course, C and D make no sense because we're talking about the heat of vaporization of ethanol. Heat of vaporization is the energy needed for the phase change. We start here and end it here. We can see that it takes a lot more energy for the liquid to become a gas than it would be for what? A solid to become a gas. So the lines right here on the flattened ends, the lines of these plateaus represent the phase changes. And you notice this line here represents this amount of energy. It's called the heat of fusion. And they go from here to completely vaporize a sample. That's the heat of vaporization. That line should always be bigger. Okay, again, understanding the wrong answers are just as important sometimes as the right. 14 is A. Okay, number 15, we're looking at the triprotic acid, phosphoric acid that we titrated in lab, and we have 3 different Kas that we found. Okay, this should be times. Okay, so these are just the Kas. Now, what do I know? Well, I know that I have a solution prepared by mixing 50 milliliters of sodium H2PO4. Now, sodium in front That's screaming to me that sodium, because of many reasons that we've already talked about, is always a spectator. It's got a big ion, it's only positive one, low attractive forces, is going to dissociate into free sodium ions and make the H2PO4 negative 1. There was only one sodium, so only one came off, so now you've got that one negative charge. Now you've got the other salt, Na2HPO4. That's going to dissociate into, well, two sodiums come off, so two positives come off, so that becomes HPO4 negative 2. Okay, so we're basically adding both of these acids, conjugate acids, to a solution. On the basis of the information above with the Kas, which of the following species is present with the lowest concentration? Well, looking at H2PO4, I see that this has a pretty low Ka, okay, but compared to HPO4 negative 2, my gosh, it's much bigger. H2PO4 barely dissociates. So this will go forward somewhat, make some of this, right? Not a heck of a lot, but this is going to barely make any of this, right? Because you compare these two Kas, this one, okay, a magnitude of what, 10,000, 100,000 times smaller. So if you look at these choices, this acid here, okay, is barely going to go forward. Now this one will go forward barely as well, but it will make some H2PO4. So clearly by making some H2PO4, all right, you can see that this one is going to be smaller, probably, definitely, than this one. But you can't pick HPO4 negative 2. This is what they call a great distractor. Many people looking at this and going fast would say C is the answer, because this one barely dissociates. So most of this, because of its smaller Ka, okay, it barely dissociates, meaning more reactants are favored, then this must be in greater concentration. Okay, but you have to be careful. Look at your choices. Look at this guy right here. If this barely goes forward, barely this is made. So of all the choices, because this one has the highest or the smallest Ka, it favors the reactants the most. The least amount of products are made. This chemical right here is going to be in the smallest concentration. So if you were just thinking in terms of the two conjugate acids that were added and the sodium ions, which by the way would be in the greatest concentration because they would completely dissociate, okay, it's easy to see you picking C, okay, no pun intended there. But duh, D is the answer because of clearly this is the least amount of product. Remember, small KSP, Ka, I keep saying that, smaller the Ka, I mean it parallels KSP in the sense that KSPs are small. But the smaller the Ka, the least amount of products being made. Why? Because Ka, KSP, KQ, it's the concentration of products over the reactants. And if you've got a small equilibrium constant, that means your reactants are big compared to your products. So D is the answer. Number 16. Okay, number 16, we've got a reaction at equilibrium. They're giving me the equilibrium constant. They're calling it Kp because these are gases. They could call it a Kc if there were concentrations. It doesn't really matter, okay? So we've got a certain gas decomposes. They're giving you, at some point, this is the concentrations. They're not saying that these are the concentrations at equilibrium. Certain gas decomposes, as represented by the equation above. A sample of each of the three gases is put in a previously evacuated container. So they're putting these in before they get to equilibrium. That's a very important key here. By knowing that you're putting these samples in before you get to equilibrium, what we know is that these values could be calculated into a Q value, a reaction quotient. Now the temperature is held constant. In which direction will the reaction proceed? Knowing the direction or asking for the direction is what I keep doing here. You have an equilibrium position and we need to evaluate our Q. If our Q is what? Less than K, it's going to go forward. If our Q is what? Greater than K, it goes in the reverse. Okay, so let's go find our Q. Now what's Q? Products over reactants, coefficients become exponents. Solids and liquids do not apply. These are all gases, So it becomes X, and I'm using parentheses because there are gases, okay? And I'm going over XY. And because this has a coefficient of 2, it's squared. Again, we don't have a calculator, but we can handle this. This is not a big deal. Okay, XY is 0.01. Okay, 0.01 squared, okay, is going to become 0.0001. Okay, I'm going to add 2 zeros. Okay, so you should be able to figure that one out. And that's over what? Well, we're going to take the sum of, or not sum, the product of 0.2, right? X squared is 0.2 that goes here, times y squared, 2. So 2 times 2 is 4, okay? And we deal with the decimal because this has none, this has 1. It's 0.4. I think we can handle that. Okay. Now the question is, this is the value for Q. Is this bigger or smaller than 230? Okay, and I know some people are more mathematically inclined, but this is 1,000th. Okay, if you're dividing by 1,000th, it's the same as multiplying by 1,000. Okay, so when you do that, multiply. Actually, this is 10,000. My bad. I know my math really well. So this is a 10,000th. So when I'm dividing, because this is the tenths place, the 100th place, the 1,000th place, is the 10,000th place. I can do this. So I'm going to multiply the top number by 10,000. And so my Q is going to equal 4,000. And maybe you saw this already and you didn't need my herky-jerky explanation, but clearly Q is 4,000 and my K is 230. My equilibrium is 230. So Q is a bigger value compared to K. So if K is 230, if Q is bigger, in this case it's 4,000, then it's going to go in the reverse to spontaneously. We always move toward equilibrium. So if Q is larger than K, I love these diagrams, now it's going to go backwards to go toward K. So clearly this reaction is going to go toward the reactants. Lower the, we have too many what? Too many products and not enough reactants as compared to equilibrium, so the reaction is going to move and shift that way. That's what basically the Chatelier's principle is, Q versus K. So the reaction will form more reactant. We say reactant because there's only what? One there, okay? So that's how that works. Now there's other choices there. The mixture is at equilibrium, so there'd be no change. No, they're saying it's important. C is not the answer because the sample of each of the three is put in a previously evacuated container. It didn't get a chance to react yet. It cannot be determined unless the volume, no. We don't need the volume. We can use the partial pressures, okay? That's what the parentheses are. Okay, so B is the answer for 16. Number 17. Okay, number 17. My gosh, a titration curve. I love it. Okay, so we've got a 0.35 gram sample of lithium placed in an Erlenmeyer flask, 100 milliliters of water. Okay, basically we drop the very reactive alkali metal, which we should all know, with water is going to be very reactive, produce a lot of heat and hydrogen gas. But what also it does is that lithium, who has that electron that it loves to push off, is going to be pushed off on that electron deficient H, who has its electrons kind of closer to the oxygen. That's why H hydrogen bond. So this thing is like a proton. And so the hydrogen will grab that electron and make an H with an electron. And what you're left is with hydroxide ions that are negative. And if you do this twice, you have two H's doing that, and they'll come together and make hydrogen, or H2, but more importantly, they make the hydroxide ion. So this is going to make a base. So when you take the fluid after this reaction and you titrate it by dropping a monoprotic acid, we get a nice titration curve here. Now this titration curve shows me that clearly I've got a weak acid here because I've got my buffer region that we're probably going to use. But back to the question, all right, so which of the following changes will most likely increase the rate of reaction? Now what factors increase the rate of reaction? Anything that helps increase the number of collisions that will basically in turn increase the number of effective collisions. Effective collisions means that you have enough kinetic energy to overcome the repulsive forces of our electron clouds, and that you're hitting in the proper spot or orientation, especially in big molecules. But if you increase the number or the frequency of collisions, you will increase the number of effective collisions. But in this case, What does that? Well, look at our choices. Using more water. Well, using more water would probably um, uh, not be a factor because it's about how much lithium. Lithium is the limiting reagent here. Water is in excess, right? Because you kept doing it until the lithium ran out. Using a smaller gram sample instead of a bigger, well, the rate of reaction would probably slow down, but the best answer in terms of increase the rate of reaction, I would say would be increasing the temperature, which is not a choice. You make the collisions go up, but C is the best answer here because you're going to cut the lithium into smaller pieces. And if you remember your basic chemistry, you're going to increase the surface area. And by increasing the surface area, you're exposing more atoms of lithium that can now collide with the water, or the water now can collide in the crystal of more lithium atoms if you cut into small pieces. That's why carbon dust is explosive, and all the reasons we've talked about grain elevator explosions. Decreasing the temperature would decrease the rate, okay? Using more water, okay, probably would not have any effect because it's about the limiting factor of the lithium. And then using less grams of sample would lower it as well. But the best answer to increase is increasing the surface area. 17 is C. Number 18, what will be the effect on the amount of gas produced if the experiment is repeated using 0.35 grams of potassium instead of 0.35 grams of lithium? Okay, now, as we understand, we know that potassium, we have lithium, we have sodium, and we have potassium. These are alkali metals that are in the same column. And as we know, when they go down, they actually get more reactive. But that's not what this really is about, okay? What this is about is the fact that 0.35 grams of potassium will give me a different number of atoms as 0.35 grams of lithium. Well, why? Well, when you look on your reference table, you'll see that lithium has an atomic mass of 7 grams per mole, approximately. I'm just reading from the gram atomic mass, right? Just the mass. And then potassium has a gram atomic mass of 39 grams per mole after I round off. Okay, so what does that mean? For the same mass, okay, because the molecular mass is, or the gram atomic mass is smaller for lithium, you've got more moles of atoms of lithium. And you can just do that. 0.35 over 7 will give you a bigger number than 0.35 over 39. Of course, I know you don't have a calculator, but the smaller the atomic mass for the same mass, the greater number of atoms or moles you're going to have. So you're still going to produce hydrogen gas, okay, but it's going to be less than that produced with the same amount of lithium. That's why B is the answer, okay? It's all about understanding the atomic mass there. Yes, potassium is more reactive. It's going to react faster, okay, but it won't produce nearly the same amount of overall hydrogen because there's less of it. We would need 39 grams to have 1 mole of potassium. You need only 7 grams. So for the same mass, there's more lithium atoms. Number 18 is B. Number 19. For number 19, on the basis of the pH titration curve, the pK value of the acid is closest to what? Gosh, this is another question. If you guys are so weak in acid and base, you've got to get it down. Another question using pKa's and pH equals the pKa. All right, we got to know this, all right, that the pH equals the pKa. So what is this max buffer I just mentioned? I say max buffer because, and it's a word I use because it represents that I have equal amounts of the conjugate base and the conjugate acid. And when you have equal amounts of these two, you get the max buffer potential because you can equally buffer any extra base with this acid or any extra acid with this base. So that's what I mean by max buffer. Now I also mentioned to my students max buffer position. When these are equal, something very special occurs, and that's pH equals pKa. And as I keep saying, it pops up all the time. Now why? Because when you use the Henderson-Hasselbalch equation, pH equals the pKa, plus the log, okay, of the conjugate base concentration, molarity, over the concentration of the conjugate acid. When these values are the same, of course, they become the log of 1, and the log of 1 goes to 0, and you're left with this value. So the question is, where can I see where the pH equals the pKa? And where is this max buffering position when these values are equal to give me this relationship? Is a beautiful place on the titration curve to show you. Let's go there. So when we look at this titration curve they give us, the first thing that I grab is I find the equivalence point. I find that more asymptotic line right here, and I find that middle position between the two bends here. And I'm going to estimate right here. And the one thing you should recognize here is that equivalence point where the H pluses, or the protons, equal the hydroxides. That's where the equivalence point is above 8. And this tells you that we have something called a weak acid, okay, and a strong base titration. Okay, and that weak acid produces a conjugate base that can pull protons from the water to make more hydroxides. That's why the pH is above 7. Okay, something you should really understand here. Okay, let's get rid of some more stuff here to clean up the points I want to make. Now, if this is the point, okay, where all of the base being added, I know base is being added because the pH is rising. So if you want to have a visual, think of, I'll get rid of that. Think of the acid sitting in a beaker. Okay, so think of, I have my acid, my weak acid, sitting in a beaker. Okay, and then I'm dropping hydroxides, let's say from a burette, that's going to pull the H's and force the hand of the weak acid to make what? To make conjugate base hanging out. That's important you realize. Every drop of hydroxide pulls an H away from the what? Weak acid, and makes a conjugate base. You have to understand it. It's that conjugate base that drives the pH above 7, because that conjugate base will pull an H away from water and do what? Reform the acid and produce a hydroxide. It's something you need to understand. And because it produces hydroxides, it pushes the pH of the equivalence point above the 7. Now, what I want to show you is understand that for every drop or every hydroxide added, we produce conjugate base. And one way to see that is through a Stoich table. This is not an equilibrium table, but let's do it nonetheless. So let's make up some fake numbers here to show you where would that max buffer position be when these are equal. Well, let's pretend I'm in a beaker and I have 1 mole of my weak acid. And then, well, if I have my max buffering, I'm sorry, my equivalence point to be here, and let's draw a relatively straight line. Okay, I guess if I try to figure this out, it's about 25. So it took 25 milliliters of the base to completely neutralize my what? Acid. Then you should see half that value would be the halfway point. That's the max buffer region. This is the buffer region right here. Where is it where I have equal amounts? Well, if I needed exactly the same amount of hydroxide to neutralize the acid, halfway would be the halfway point. And that's the max buffer region. So half of 25 is about 12.25, and I'm guessing it's somewhere around here. And draw my almost straight line up. This is the point I'm looking for. Now, I want to show you, because I want you to understand that you need to understand that what is this halfway region? How do we get it? Well, again, if I had 1 mole of my weak acid, and let's say I'm at the halfway equivalence point, which I like to call max buffer, they call this, we'll make this 0.5 moles. And let's pretend we have none of this available. And then, of course, the limiting reagent, of course, is the base. So it's negative 0.5 moles. Negative 0.5 moles, and this is plus 0.5 moles. Okay, stoichiometry is 1 to 1. And what am I left with? I'm left with, well, 1 minus 0.5 moles, I'm 0.5 moles or left. This, of course, goes to 0, and this is 0.5 moles. And you can see clearly, hopefully now, that when I have the half the amount of base needed to neutralize the weak acid, I produce equal amounts of conjugate base, and I'm left with equal amounts of acid, okay? And that will give me a halfway equivalence point, which I call max buffer, because I have equal amounts of acid and base, and because I know the pH equals the pKa when these values are equal, then I can just take half of the equivalence, read off my graph, and find my pH. All right, and my pH is equal to the pKa. And it's closer to 5 than it is to 4. It's pretty close to 5. I guess it's a little higher. Pretty close to 5. Okay, you can see 4 is on this line and 5 is in between somewhere. So definitely close to 5 despite my crooked lines I'm drawing here. All right, so that's how we do it. A lot of explanation there for something that's very simple. Okay, in a buffer region, the max buffer region, the halfway titration point, I call it max buffer. So 19 is choice B, number 5. Okay, now number 20. Which of the following is the balanced net ionic equation for the reaction between lithium and water? Okay, well, we should realize we're making the hydrogen gas. We're making a base, lithium hydroxide, but we're not going to write lithium hydroxide like this because it's a strong base. Okay, so that doesn't make any sense. It's going to be broken up. So the best choice here is choice B, where I have the solid reacting with the water. We keep the water together, not broken up, because water is a terrible electrolyte. It doesn't like to break apart. I know that because its Kw is 10 to the negative 14, very small. So its ions as its products don't really happen, so I keep it together. This is going to make a lithium hydroxide on paper, but it doesn't stick together because it's very soluble. Group 1 ions like sodium, potassium spectate. So this will break apart as an ion, but I have to show it because I have lithium solid over here. Okay, so B is the best answer. All right, and the rest of these are not showing the base. This one is correctly, but too many hydroxides. So this one's not balancing A, so 20 is B. Number 21. Benzene, drawn right here, okay? Consider the observation that benzene is only sparingly soluble, barely soluble in water. Which of the following best describes the intermolecular forces? Okay, the IMFs. Okay, so again, we're not talking about the bonds between the atoms. We're talking about the attractive forces between, let's say, benzene and water. Okay, so we're talking about any type of attractive forces. Now, there are some because they're sparingly soluble, so there must have or share some similar IMFs. Now, understand, if we're talking about solubility, it's because molecules, okay, share some similar attractive forces from other molecules. It is not about the bonds. So I immediately, anytime I'm talking about boiling point, melting point, phase changes, physical changes, vapor pressure, I'm not talking about bonds. So I'm getting rid of 2. Okay, so now what does this mean? Well, think about the intermolecular forces of attraction that must be similar. Water we know is polar. We know it has dipole forces, okay? So because of its polarity, it's got a negative end and a positive end. We know it has dipolar forces. We know it also has hydrogen bonding because we have that electron deficient H out there with the O and an F, okay? So we know there's H bonding. And all chemicals have LDFs, and LDFs are London dispersion forces. This is due to the cloud of electrons that the oxygen has and the cloud of electrons that the benzene has. So because these have LDFs, that's the magical part here. Now, of course, looking at benzene, It is not polar. If it has any dipolar forces, they're almost insignificant. Okay, it has no H bonding. These H's are not electron deficient. Okay, because they have to be bonded with an oxygen, fluorine, or a nitrogen. So the only thing that's got going for it, it's got a big cloud of electrons. So all it has essentially is LDFs. So that would mean that water and benzene will interact only by London dispersion forces, which, by the way, is based upon the cloud of electrons that this molecule has. And if this cloud can be deformed a little bit, meaning if the electrons can move to one side a little or other, just a little bit, can give it some very, very partial polarity. Okay, and it's momentary, meaning as soon as molecules move away from it, it'll turn off. So let's pretend the negative end of the water comes in contact. Well, what's going to happen is these negatives in the cloud of electrons outside the molecule could slightly deform the cloud and move away. By moving away, you create a place that's partial positive a little bit. Now, we wouldn't say it becomes positive, but because of electrons being repelled and this cloud shifting over, you create a place with less electrons, and that would be a slight polarity, that would be a slight attraction, that would make it sparingly soluble. So the only thing they have in common is LDFs. So look at your choices. Benzene is nonpolar, therefore there are no forces between. Absolutely incorrect. There are some forces because all chemicals have a cloud of electrons. All chemicals will have LDFs. And LDFs, although weak because of the momentary charges, can become pretty significant. Okay. C, benzene is hydrophobic. Well, in AP Bio, we would say, yeah, that's true, but it's not because there's a net repulsion. They don't repel each other, okay? They just prefer each other's attractive forces. Water prefers to H-bond with itself. That attractive force is much stronger, so therefore water has a tough time breaking apart its own H-bonding, its attractive force, to actually make some interactions. So it's more of them basically preferring each other own attractive forces. So the best answer is D. There are dipole-induced dipole and London dispersion forces. This dipole-induced dipole just means that, just as I said, as the water moved in, it made this electrons move, okay, and induced a dipole. But some people consider that to be a London dispersion force too. So it induced a partial negative. So some people call that an induced London dispersion force. It doesn't matter. They're all the same thing. D is the answer. Number 22, you can't get away from acid-base chemistry. You just can't. You can't hide. You have to know these problems. Got to dig down deep and figure these out because they're all over your tests. Okay, in this question, they gave you two Kas. Now, Ka is just like any other KEQ. It's products over reactants. Coefficients become exponents. Solids and liquids do not apply, and they give you who is favored when this reaches equilibrium. So a very big equilibrium constant, or in this case bigger than this smaller one, means that there's more what? Products favored. So this is a stronger acid because I can see that the Ka is larger here. Larger Ka means there's more products. And what are the products of an acid? The products of an acid are its conjugate base and the proton. If we're in water, we would say the acid with the water, and again, you could do this either way, it'd be fine, would be the hydronium ion. These guys, of course, are synonymous. So higher the Ka, stronger the acid. So looking at these Kas, this one being smaller tells me that the reactants are favored. And the reactants are the acid's concentration, which means it barely likes to dissociate if there's the least amount of products here. So this has the smaller Ka, it has the greatest amount of reactants, and if you make your denominator bigger, the equilibrium constant will be smaller. It's important you understand that. Okay, so I know that this one is the weaker acid of the two. Now, what do we know? Well, in this question, they're saying which of the following is true about the pH of the solutions at equivalence point. Now, I mentioned this in question 20. When you looked at a titration curve, knowing what the pH of the equivalence point tells you something about whether it's weak acid, weak base, so forth and so on. So how to break this down is I'm going to take this weak acid, and it basically is vinegar or acetic acid. So CH3, I'm going to write it this way, OOH, okay? And basically what's going to do in a strong base with, okay, they're adding a base here, titrated with a strong base, so it's a hydroxide. The sodium is spectating. This strong base is going to yank an H away, and I'm left with this what? CH3COO negative. And of course, I made water. Okay, so this is my conjugate base. There's my A negative, and there's my HA. Okay, now, what do we know? Well, at equivalence point, I added equal amounts of these guys. All right, so if I add equal amounts at the equivalence point, both of these guys no longer exist. Okay, now I'm not going to do the math, but we could clearly do the math to figure out the molarity. But we added equal amounts, so all of this is gone and all of this is gone, and we have 100% conjugate base. That's what the equivalents mean. We added enough base to completely wipe away all the acid. Okay, and if you do a titration curve, and I keep showing you these, you're going to see this buffer region, and then you're going to see the equivalence region. Okay, because it's a weak acid base scenario. But at this region, we have 100% conjugate base. Okay, now why would the pH not be at 7? Well, it's not going to be at 7 at the equivalence point because we have a remaining conjugate base that can ionize water. If this is a weak acid, it produces a stronger conjugate base. How do I know that? Well, I know that because if I know the Ka is high, now it's not really that high, it's low, but I'm just giving you an understanding of this. The Kb is low because Ka times Kb equals Kw, which is 10 to the negative 14. So in this case, we had a weak conjugate acid. So that means the conjugate base is Kb has to be higher. This Kb is the ability for it to grab a proton. So weaker the acid, that's the arrow down, stronger for the ability of the conjugate base to grab a what? An H. Let's look at that reaction. So let's put, now, once we have created a scenario where we've driven the acid completely, okay, to its conjugate base, what do I have left? What I have left is I have the conjugate base, CH3, COO negative. It's sitting in water because there's no acid and base left, right? The predominant species is in water. And just as I mentioned, if this is a weak acid with a low Ka, it must have a pretty high Kb, relatively speaking, which means it has an ability to yank an H, act like a base, grab a proton from the water, and make what? Reform the acid. But more importantly, when you pull the H away from the water, is you produce a hydroxide. And that hydroxide that gets produced because of the conjugate base being produced at the equivalence point and it having an ability to pull an H creates a scenario where your pH is greater than 7 at the equivalence. Now, none of these are strong acids. And I'll mention this again. Strong acids and strong bases have conjugate acids and conjugate bases that have no ability to pull H's or protonate the H's. They have none. Why? Because they're strong acids, strong bases. If their conjugate acids, conjugate bases had an ability to go in the reverse, then they wouldn't be a strong acid. So strong acids and strong bases always go a pH of a 7 because their conjugate acids and conjugate bases are too poor. They can't do anything with water. It makes sense. If you've got a strong acid with a high Ka, its Kb is so small it has no ability to ionize water and produce a hydroxide. So, given these two weak acids, this being the weakest, the lowest Ka, it would produce the what? The highest Kb. And therefore, solution 1 is going to have the strongest conjugate base that's going to produce a bigger pH and more hydroxides because it's great ability to pull H's from water. And therefore, at the equivalence point, solution 1 has a higher pH because this has a stronger conjugate base. Choice B. You really need to look this over, review this question. As I keep saying, acid and base is going nowhere. 22 is B. Number 23, a 1 gram sample of a cashew was burned in a calorimeter containing 1,000 grams of water, and the temperature of the water changed. It went up, so heat was released. In another experiment, a 3 gram sample of a marshmallow was burned in a calorimeter with more water, and a temperature increase that was similar. Based on the data, which of the following can be concluded about the energy content for 1 gram, it's important, of each of the two substances? Okay, well, we do know that we're dealing with Q equals MC change in T. Now, they're saying which one is going to give off the most energy per 1 gram. That's key. So if I break this up, I know that in half here, on the cashew side, what do I have? I have 1,000 grams of water. Okay, and I've got a temperature change that's 5. Okay, and I know that I have a specific heat. And on the other side, I have 3 grams of marshmallow. I have 2,000 grams of water. I've got a temperature change of also 5. And I also know that Q equals MC change of T, my molar heat capacity or my specific heat is right there. Okay, and we could certainly do all this math, but again, you don't have a calculator, so really understand some tricks here. Because there's specific heat in water, my calorimeter is about the same, I'm not even going to consider it. Since I'm just trying to evaluate who is going to have more energy, and I'm not looking for a number, I'm not going to actually find this value. So I'm going to leave C out because it's being multiplied by both of them. I'm just going to see relatively who's going to be higher. So I'm going to take 1,000 times 5, and that gives me 5,000 joules. I know C is not 1, but it's a relative amount. And this would be 5 times 2,000. This would be what? 10,000. Okay, so you can see, wow, more energy for the marshmallow. But remember, they were looking at per gram. They didn't come out and say it, but they wanted it per gram. Now, the cashew was already 1 gram, so that's our value. But there was what? 3 grams for the marshmallow. So divide this by 3, and you can see that 10,000 divided by 3 is approximately going to be what? 3,333.33. Okay, so this dividing by the 3 grams, okay, is going to give me a value of what? Energy per gram. This was already there. So when I compare this value to this value, clearly the cashew produces more energy. Okay, so the answer to my question is the combustion of 1 gram of cashew releases more energy than the combustion of 1 gram of marshmallow. Even though we did not combust 1 gram, by knowing it was 3 grams and dividing my total energy by the 3, I got a value that was per gram. And again, I didn't need to actually find this number because C is the same on both sides. We're getting a comparative value. This isn't really the true value, but I'm getting a comparative value. So 23 is C. Number 24, another particulate diagram or illustration question. You should jump on these and say thank you very much. So we've got a reaction between NO and O2, okay, to produce NO2 in a rigid container. Imagine that. Okay, pressure in the container is recorded using a pressure gauge, which the following statement correctly predicts the change in pressure as a reaction goes to completion at constant temperature and provides the correct explanation. Well, if you look carefully, we've got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 gas particles. And now we have what? 1, 2, 3, 4, 5, 6, 7, 8. We have less particles as atoms combined. So if you've got less particles for the same volume, same temperature, the pressure has to drop. PV equals nRT. We solve for P, nRT over V are what? Volume stayed constant, temperature stayed constant, universal gas constant. So the number of particles decreased, that's my N, the pressure decreased. It's pretty intuitive. You really do not need the ideal gas law formula, but hey, I guess I'm showing off. So the pressure will decrease because there are fewer molecules, okay, than what? Than the reactant. So we produced in the process of this reaction going forward, no equilibrium, less particles hitting the side of the container, less force, less pressure. Okay, 24 is B. Number 25. So number 25, we have this kind of grouping of questions that are happening. You're going to see that on your test day as well. And I suggest you go right to the question first. You may want to look this over. They're giving you thermodynamic quantities and they're giving you some time, but I really would go to the question. Sometimes you get lost in the shuffle. Whatever works for you, but really got to get to the question. Timing and pacing is important. So I'll go to 25. Which of the following identifies the elements being oxidized and reduced in the reaction? Okay, so here's my reaction. And now I'm going to need to understand who got oxidized and who got reduced. Well, since I only have one reactant, okay, the key is going to be right in that one. So really what help to figure out who is oxidized and reduced is to write oxidation numbers. So H2O2, very basic skill. Okay, let's go find the oxidation numbers. Now this 2 in front has no bearing on the individual charges of these elements in the compound. Now, some people already know that in a peroxide, oxygen is -1, but if you don't know that, the H in front has to be the positive one because of the more electronegative oxygens pulling electrons away. So oxygen can only lose an electron, so this we know is +1 individually. There's 2 of them, and the way that I always did it, and I tell my students, is the total charge of this is 0 in this case because there's no charge. It's not a polyatomic ion. So this whole thing has to equal 0. So each H has to be +1. Overall charge is +2. The whole thing has to equal 0. So overall charge due to all the oxygens has to be -2. And because there's 2 of them providing a -2 charge, each oxygen is -1. So now I know oxygen is starting at -1. Okay? Now, what happens in water? Okay, well, if I look at water, H2O, do the same thing. H is my +1. +2 overall, whole thing has to equal 0. So this has to be a -2 overall. There's only one oxygen. Hey, each oxygen is -2. So in the case of H2O2 going to water, okay, in this instance, we have an O who is -1 in the what? Peroxide, going to an O who is -2. How did that happen? It happens because this thing must have absorbed an electron. And when you absorb or gain electrons, we call that GER, if you remember that. That's reduction. Reduction means your charge drops. A -1 goes to a -2 because you got reduced. So this, of course, is reduction. So we would know that what got reduced? Clearly the oxygen is reduced. Okay? Now if we look at O2, we know that anything in the elemental state or bunch of the same type of atoms or a standalone atom has a 0. So if we go to the next one, we have an O0. Oh, I'm sorry, my bad. We have an O-1, which is the only place where we have oxygens in the reactant side. So that's O-1 again, is going to go to the oxygen, which is 0. How did that happen? That happened because we must have, what? Given off an electron. And we call that LEO, or losing electrons. LEO, the line says GR, so this is an example of oxidation. Oxidation means we've lost an electron, which increases our charge. Reduction means that your charge went down because of gaining electron. Oxidation means that your charge goes up because you lost, because you're producing an electron in the product side. So in this case, oxygen is both oxidized and reduced. Sometimes we call this a disproportionation reaction, where the same species gets both oxidized and reduced, and here's a great example. So this is a redox reaction where the same chemical got oxidized and reduced. So 25 is C. Number 26. Maybe. Okay. The O2 produced from the decomposition of a 1 liter sample of H2O2 is collected in a previously evacuated, love to say that, don't they, of a 10 liter flask at 300 Kelvin. So they produced some oxygen in the reaction. They had a liter sample of the H2O2, all right, and they collected it in a 10 liter flask. So we're going from 1.0 liter container to a 10 liter container. That's important in this problem. The volume is increasing 10 times. Now they're collecting the oxygen and putting it into a bigger flask. And notice the temperature is staying constant. It's at 300 Kelvin. It's important that we recognize all these things. Okay. And this was at 300 Kelvin as well. So our temperature is staying constant, and we're collecting the oxygen from this reaction that originally occurred, okay, in a 1 liter sample. Now they said, okay, in the problem, what is the pressure in this flask, in the new 10 liter flask, which we know is 10 times bigger than the original 1 liter flask, okay, at 400 seconds. So that's key. We have to go to 400 seconds in the reaction. So when I go to 400 seconds, what I see is that there is 1.7 concentration left of my hydrogen peroxide. Now it started at 2.7 and it went down to 1.7 in this after 400 seconds. So we can clearly see, I know we don't have a calculator, but the math is easy to find out how much changed. So when we do the reaction, okay, you can clearly see that there was 2.7 minus 1.0, I'm sorry, 2.7 minus 1.7, kind of giving the answer, right, equals 1.0, and this is a concentration, so this is molarity, okay? That's how much was lost. So if I go to the reaction, and let's write it again here so we can clearly see, because this problem a lot of people got wrong, okay? So if we have H2O2 decomposing in that redox reaction, and we make O2 and we make the water, okay, and we balance here, what we think here is that, okay, originally there's a loss. This went forward, okay, and as we said, it originally had 2.7 value, right from the table, okay. It originally at time 0 we had a 2.7 molar concentration, and now we're 1.7. So the difference in this time period is that there's a loss of 1, subtracting those two numbers. So I can say what? Minus, okay, if you want to do this to see it, minus, okay, 1.0 molar, and this would be what? Plus 1.0 molar. Look at the ratios here. This is 2 to 1. So it's not a minus x plus x. This has to be what? Plus 0.5. Why? That's important. That's what this problem was getting at. Can you see the stoichiometrical difference here? So stoichiometric difference. This is a 2 to 1 ratio. So this lost 1. This didn't gain 1. It gained half as much because the coefficient is 1. That's very important. All right. So we know that we now have in that 1 liter flask 0.5 molar, which means I have 0.5 moles in a liter, right? It was a liter container. The reason why they made it 1 liter, so you recognize it's 0.5 moles. Now, okay, what would be the pressure? Well, the question said for estimation purposes right here, they wanted you to use this. Assume that 1 mole of a gas at 1 liter exerts a pressure of 24 atmospheres. So that would mean that if this was a 1 liter container for the gas, this would be 24 atmospheres if it was 1 molar, but it's half a mole. So it's half that, so it's 12 atmospheres of pressure that would exist in a 1 liter evacuated flask that just had the oxygen. Okay? But, and this is the most important part of the problem, okay, this 0.5 moles was now placed in a bigger container by 10 times. What's molarity? Moles over liters. Because we have 1 liter here, it was 0.5 moles per 1 liter. This is 0.5 moles, okay, in 10 liters. So what's the concentration now? Okay, you can see it's because you're putting the gas in 10 times the amount of space, okay, the pressure is going to go down by what? Divide by 10, or the molarity. So this is really a what? A 0.05 molar, okay? But the bottom line is I've got 12 atmospheres of pressure that would exist in 1 liter. If I make it in 10 liters and I divide by 10 because the space is bigger, you can see that my pressure now would be 1.2 atmosphere. So let me review this. Okay, we produced 0.5 moles of gas in this reaction. Why? Because we noticed we lost 1.0 moles or molarity per liter. So we can just say it's moles because it per is 1 liter. We gained 0.5. This is what the table told us. So I've got 0.5 moles in a liter. Okay? They told us, very important, right here. They told us what? They told us that for every 1 mole of gas, there's 24 atmospheres. So in my 1 liter container, okay, in 1 liter, a mole of gas is 24. So because I had half of that in 1 liter container, right? I had half of that, which is 12. Okay, so really I had 12 atmospheres. Because you put it in a container that was 10 times bigger, okay, then my pressure is going to drop 10 times because now I'm going to, basically the gas is going to expand as an ideal gas would into the open areas. And so I take my 12 and divide by 10 and I get my 1.2 atmospheres. And that's why A is the answer. A tough little problem there, okay, that needed for you to see the stoichiometric relationship and make some estimations and understanding that when I made the volume 10 times bigger, the pressure was going to drop 10 times. Has to. Pressure is a force over area. If I make the volume bigger, the area is getting bigger, okay, the force or the pressure has to drop. Okay, so that number 26 is A. Little tough problem there. Number 27, which of the following statements is a correct interpretation of the data regarding how the order of the reaction can be determined? Since I do not have data that tells me about how did the rate change if I change the initial concentrations, all I have is a plot of time and how much my initial concentration, I have to realize that I'm dealing with either first or second order. That's all I have in this course to deal with. Now, how do I deal with that? Well, very simply, you need to recognize from your 2 formulas. Your 2 formulas are given to you in your reference table. In your reference table, you have something called the integrated rate law formulas. And they look like this. They have the natural log of A, okay, of some time period, minus the natural log of the concentration of your A or reactant, A, at some 0 time period equals negative KT. They give you that one, and they give you 1 over the concentration of your reactant some time period minus 1 over the concentration of some initial concentration equals positive KT. They give you them right in order like that in your reference table. This is the first order since the first one written. This is the second. Okay? So what do we know? Well, if I manipulate this and put this and this ln of A0 on the end, all I do is by adding plus ln A to 0 to both sides, what I get is this plus the ln of A0. And what I get is y equals mx plus b. Yeah, I get a straight line, but it's going to have a what? Negative slope. So they're saying, how could the order be determined? Well, the reaction must be first because there's only one reactant species. That's wrong. You could have something called zero order, okay, if it's just one reactant. You don't have to have first, second. It could be zero, first, second order for that scenario. The reaction is first order if the plot of the ln of, that's our A, okay, versus time is a straight line. They were nice. They didn't even say negative slope, and that's why that's the answer. The reaction is first order if it's 1 over A. That'd be second order. And for the reasons I've explained here, if I move this up a little bit, okay, if I do what? Add a positive 1 over A0 over to both sides, that would cancel on the left-hand side and give you this. What do I have? Y equals mx plus b over here. This would be a positive slope, straight line, because I have a linear equation. And it'd be a positive slope if I'm plotting the 1 over A, which would be hydrogen peroxide. That would give me a value something like this. Okay? So the reaction is first if the plot of the 1 over is a straight line. Okay? That's incorrect. It would be second order. All right, so that's why C is not the answer. And the coefficients never tell you the orders unless you know it's an elementary step. If it was one step, we can't look at any reaction given to us and assume it's one step. We would need some data, a mechanism, or some way to look at this. So when they give us reactions, they're overall. So you just can't assume because the coefficient is there. If we know it's an elementary step, then we can. All right, so B is the answer. This stuff pops up every test, guys. You have to be able to get the graphs of these. Now, if they give you a question and they give you the graphs and the graphs are not a straight line, it can't be that order that we're looking for. Number 28. Number 28. The reaction is thermodynamically favorable. Ding, ding, ding. They just told me something. Delta G is negative. Okay, that's an important statement they just made because you know what? They can ask for that also in part 2, free response. Show me with proof why something is thermodynamically favorable. They're talking about a negative delta G. Okay, so they're saying that delta G is negative by making that statement. The signs for delta G and delta S of the reaction, which are the following. Well, first of all, they just told me that indirectly, so I know that delta G has to be negative. What about delta S? Well, delta S for the reaction. Let's look at the reaction. Okay, and what do we have? And we have 2 H2O aqueous. We have 2 molecules that are aqueous. They become 2 liquid molecules, but they make a gas. Okay, so I've got 2 aqueous molecules making 3 molecules. And one of them is a gas who can fly away. So you can see that the disorder has increased, or the delta S, that we parallel with disorder. We know that delta S is a measure of the dispersion of energy, but because gases have more kinetic energy than, let's say, liquids or molecules that are surrounded by water in a solution, we can clearly see that energy has been dispersed, or we can say that the randomness of the system has increased, or the entropy has increased, and therefore we call it a positive value. So it's just that simple, that the delta S of the reaction is positive, and they love to ask that in part 2, and the reasoning is we can say that 2 reactant molecules became 3 product molecules. Or you could say that aqueous molecules became a gaseous. I like this one, but it doesn't matter. The bottom line is you get the answer. Now, delta G, let's just do this for fun, is equal to delta H minus T delta S. If this is negative, and we know in the reaction that the delta H given to us is negative, all right, then I know it's exothermic, energy is given off, and this is minus T, which is a positive value, and my delta S, okay, we said is positive. It must be positive because 2 reactant molecules are becoming 3. We can see here that this becomes mathematically plus the negative, and a negative plus a negative always gives me a delta G that's negative. I'll call it the always rule. So in any case, either way you look at it, 28 is B. 29. Number 29. Assume that the bond enthalpies of the oxygen-hydrogen bonds in water are not significantly different than those in H2O2. Okay, so the oxygen-hydrogen bonds in this guy is the same as this guy. Okay, based on the value of delta H of the reaction, which is about negative 200, which of the following could be the bond enthalpies, that's the energy to break the bonds, in kilojoule per mole, these are per 1 mole, for the bonds broken and formed in the reaction. Okay, so what we're trying to do is see which tablature given to us in average bond energies would be the correct one that would give us this value. So before we do that, we always have to visualize what the actual bonds are in the compounds. So in H2O2, we have an oxygen bonded to an oxygen, and we also have H's here. Okay, I call this the sunglass molecule, and we have 2 of them, so I'm going to draw 2 of them. This helps me visualize how many and what type of bonds I have, because we have to assume that all of these are going to be broken and then what? Reformed as products. And the difference in the energies of both give us the delta H. So we have 2 water molecules, and there we go with OH bonds here and OH bonds here. And then we have the oxygen, which is an O double bonded here. Okay, I'm going to leave out the dots, any lone pairs. I'm not doing Lewis dot diagrams. Okay, so what do I have overall? Well, I have 4 H2O bonds, or as I like to say, the HO bonds. All right, 4 HOs there. And then I have plus 2 what? 2 O to single bond O. And over here on the product side, I have 4 HO bonds. All right, 4 H2O. Here's an H2O bond. Here's an H2O bond. The whole water is 4 HOs, whereas the hydrogen peroxide has 4 O's, but it has an additional O to O. And then we have plus what? 1 O to O bond. So we have 1 O double bonded to O bond. Okay. Now, what is the formula for delta H with bond energies? It's a little different. It's not products minus reactants, and that's what they're trying to get you here. Okay. The delta H using bond energies is the sum of the bond energies broken, which is, of course, the reactants, minus the summation of the bond energies formed, and that's in the products. So this is where it's reactants minus products. That's what comes up. Okay, and if you do a potential energy curve, if it's exothermic, you start high going low, you're going to see the energy it takes to break the bonds and the energy it takes to reform the bonds, and the difference between those 2 values is your delta H. Okay, so which one's going to give me my minus 200? Well, the one thing I can see clearly is because I break 4 HO bonds and I, of course, produce 4 HO bonds, they kind of cancel out. The difference between the reactants energies minus the products is really these 2 values here. Okay, so I'm looking for somehow some value to give me negative 200. So I'm just going to look at the O to O values here and the O to single bond, as these will cancel out. Now remember, I have to multiply this one by 2. Okay, so what can I multiply by 2 when I subtract by the singular value here gives me negative 200? That's what this comes down to. And if you look at choice B, if I multiply this by 2, 2 times 1, 50, the individual bond energy of the O to O, and we have 2 of them, okay, in H2O2, that'll be 300 minus, because of that, okay, 1 O to O bond, okay, that's 500, and you can see that 300 minus 500 is going to give me a delta H approximately negative 200, and that's about what we have here, and that's why answer 29 is B. Okay, a lot of people got this wrong for a couple of different reasons, mainly because they forgot that when you do bond energies, which by the way, hint, 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 could appear its ugly head here, rear its ugly head in the part 2. This is something you must be aware of, that it's reactants minus products when it comes to bond energies, because of the nature of breaking bonds first that absorbs energy and releasing bonds when you gain them, when you make them happen. So you had to break this apart. Could you have used a 4HO? Sure, you would have got the same result using that. Okay, so 29 was B. Number 30. Okay, number 30, a question I'm seeing popping up more and more about what happens to pH at different temperature changes. Well, we know this. Kw is equal to the product of the what? Well, Kw is the equilibrium expression of what? Products over reactants, coefficients become exponents, solids and liquids do not apply. And what I'm writing is an equilibrium expression for the autoionization of water breaking apart into its ions. So if I look at this reaction here, we'd write the equilibrium expression here. Okay, we don't consider over the there's no reactant here because these are liquids, and liquids do not apply because they do not have a molarity. Brackets represent molarity. These are aqueous. Okay, now what do we know? Well, at a certain temperature, Kw has a certain value. It's temperature sensitive. It's 10 to the negative 14. And in pure water, what are these values? Well, they have to be equal because one water breaks apart into one of these. Stoichiometrically, it's a 1 to 1 to 1. So, of course, we figured out that the concentration in pure water at a certain temperature of H plus or protons is 1 times 10 to the negative 7. And the hydroxides, 1 times 10 to the negative 7. Very small numbers. But we would say the pH, or the what? Negative log of this 1 times 10 to the negative 7 is equal to 7, and that equals my pH, which is neutral. Okay, pH is always about the H plus, don't forget, or the H3O plus concentration. They're synonymous. But what if the pH is 6.8? Okay, well, that would mean this number, okay, has changed. Okay, now 6.8 would be 1 times 10 to the what? Negative 6.8. That number just got bigger. Whoa. So if I have pure water at 37, which is not what Kw is measured at, okay, so this number got bigger. If we're still at pure water, then this guy should be 1 times 10 to the negative 6.8 as well. And the only way that two numbers that are bigger, if they're multiplied together, that would mean that my Kw is bigger, okay? Is bigger than 10 times 10 to the negative 14, okay? So at 37, the autoionization, that's a fancy word for water doing this, okay, is larger than it is at 25. At 25, it's 10 to the negative 14. At a higher temperature, it changes. Interesting enough, the pH is not acidic. We think below 7 is acidic. The 6.8 would be the new what? Would be the new neutral pH at that temperature. And that's why we have to recalibrate at different temperatures. Okay, so if you didn't like my explanation, okay, think about the numbers becoming nicer. So let's pretend that the Kw by an increase in temperature is now 10 to the negative 16. Okay, let's say let's make it bigger, not smaller. So let's make it 10 to the negative 12. Okay, so to make this 10 to the negative 12, it just got bigger because the temperature rose. Clearly, the concentrations of my hydroxide and my proton are now 1 times 10 to the negative 6. So remember, equilibrium constants are temperature sensitive. So in this case, an increase in temperature would make my equilibrium of this ionization of water, in this case, bigger, and therefore you can see that in the example I gave you here, the pH would be 6. That would be the new neutral pH. Why is it neutral? Because you have equal amounts of protons and hydroxides. All right, so that's why B is the answer, and I'm seeing more of these types of reactions, and it's based on the idea that Kw can change. It's temperature sensitive. 30 is B, 31. Number 31, to gravimetrically analyze using mass, okay? All right, the silver content of a piece of jewelry. So we want to know how much silver, okay? We first dissolve the jewelry that's made of both copper and silver, and we do so with a strong oxidizing agent, okay? We're going to have free silver ions, and we're going to have free copper ions all over the place. Now, we would probably mass out the sample first. So we'd have a mass of the jewelry, initial. Okay, so we have the mass of the initial, whatever that might be. And then we would dissolve it into the free aqueous ions. Now, what would be the next step? Well, the next step would be to add another chemical to precipitate out. We've done this so many times. So maybe I would add silver what? I would add, not silver nitrate, but I would add, let's say, sodium chloride or calcium chloride or something where I'm adding free chloride ions. And these chloride ions, we should know, would precipitate out the silver. Now, this question wasn't about knowing that silver ions precipitate with chlorine, but we want to precipitate out using our solubility rules just one of these ions. And then we would have the silver chloride precipitate, which is a solid, and then we could do what? We could mass it. Knowing its chemical formula, we can get the moles of the silver, and then we can convert the moles of silver into grams of silver, and then we could find what? The percent mass of the total, right? This would be the total initial, and this would be the part. So we would definitely add a solution containing an anion, which is a negatively charged particle. A cation would be positive. That forms an insoluble salt so that we can actually separate it and then dry it, okay, and then mass it out using some stoichiometry, figuring out the moles and eventually grams. So D is the answer, a classic lab. You really can't centrifuge a solution to separate the heavy ions. That'd be very difficult, all right? And evaporating the solution, okay, wouldn't really work either because we would have copper and silver nitrates. And adding base, this is not really an acid-base reaction here, so D, of course, is clearly the best answer. 31 is D. Okay, number 32. Sample of a compound that contains only carbon, hydrogen, nitrogen is completely burned in oxygen to produce a certain number of grams of carbon and oxygen. Okay, well, what do we have here? Well, we have some hydrocarbon with, well, some nitrogen. So we have C, H, and we have N plus oxygen, okay, is burned in excess oxygen to make CO2 and water, okay, and some NO2. Okay, we only have grams. Now we should realize, okay, that all the carbon in the organic compound is now locked up in CO2, and all the hydrogen in the organic compound is locked in the hydrogen. So I can definitely get pretty far in this problem by looking at the ratios of carbon to hydrogen in the reaction. So what I'm going to do is I'm going to just move this a little bit. What I'm going to do is I'm going to figure this out. And how I'm going to figure this out is I'm going to take my 44 grams of CO2 and figure out how many moles of carbon I have here. Now, how do I do that? Well, if I knew that with a calculator, it's much easier, but I can do some estimations here. Carbon is 12, okay, doing a formula mass. Oxygen is 16 plus 16, so 16 plus 16 is 32, plus 12, okay, is 44. So this actually equals 1 mole of CO2. And all I did is a formula mass. From that periodic table, 1 carbon is 1 times 12. If you got to do it this way, be my host, is 12. You have 2 oxygens, 2 times 16, the atomic mass is 32. Add them together, I get 44 grams per mole. Hey, that's the molecular mass of CO2. That's the grams. So I have 1 mole of CO2. Now, look carefully. In one of these particles, how many carbons do you have? 1. So if I got 1 mole of CO2, don't I have 1 mole of carbon atoms? And that's yes. So I know that I have, I'll write this over here, carbon, I have 1 mole. That's how much I'm collecting here. All right. Now let's look at the water now. Okay. Looking at the water, let's do that over here. Now water, they said we had 45 grams. Now what we could do with a calculator is we find the percent by mass of the hydrogen. Okay. And then we could figure out how many moles of hydrogen are there. But we don't have a calculator, so we're going to do some estimations. But look how nice the numbers pop out. Watch what I do here. So I'm going to find out how many moles of water I have here. And I know the molecular mass of water, if I do the same thing, is 18. And I could do 45 divided by 18. Okay. All right. Or I can find that as actually that winds up being 2.5 moles. Now you may find that to be difficult to do without a calculator, but watch what I can do here. I know that the molecular mass of water is 18, and then for the same reasons. I have 2 H's, 2 times the atomic mass is equal to 2. I have 1 oxygen, the mass of oxygen, one of them is 16 from the periodic table, and I get 18. Now, I can do 45 divided by 18, and I can get 2.5 moles, and I can realize that there's 2 H's per 1 particle, and times that by 2, and you can see I'll get 5, okay, 5 moles, and that's how we would do this. Or if you don't like that, here's what I could have done. Now, I know that 18, out of the 18 grams, 2 of them are hydrogens, right? So if I do that, that means 1/9, okay, 1 out of 9, okay, is what I'm looking at in terms of, so 1/9 of the entire mass of 45 would give me, okay, the mass of the hydrogen. So let's think about that. Is 9 and 45, can they be divided by? You sure can. So 1/9 of 45 is what? And the answer is 5, right? Doesn't 1/9 out of 45, isn't that 5? So that's 5. So what we have is 5 grams out of the 45 grams is due to the hydrogen. And what do I know? The molecular mass of hydrogen is 1 gram per mole. Hydrogen atoms, not molecules. So I have 5 moles of hydrogen. And so I have a 1:5 ratio. The only one there with a 1:5 ratio is choice B. So that's how I did that. Now again, you could have taken the 45 grams, okay, and you could have divided by your 18, and you would have gotten 2.5 moles of water. And then you'd have to realize that in water, there are 2 moles of hydrogen per 1. So you'd have to times that by 2, and that would give you 5 moles of hydrogen atoms. Another way to do that, and that's where you get this relationship empirical lowest ratio, and that's why B is the answer. So a couple different ways to think about that. Yes, I know without a calculator makes life not as nice. Number 33. Number 33 is another tough little problem that makes you fall for some basics and some Le Chatelier's principles, I believe. This is another tough one that a lot of people got wrong. So let's go through that. We have a weak acid, HF, in water is represented by the equation above, okay? And notice it's a weak acid and it's making a conjugate base, right? Okay, this is my HA and this is my A negative. That's going to be able to reform the acid. If it's a weak acid, that means that this has a great ability to pull H's from water to reform the acid. Okay, now adding a 1 milliliter sample of which would increase the percent ionization of HF. That really measures how well HF will separate. Now, the higher the percent ionization, that would mean the more that HF goes forward. So they're trying to say which one is going to create a scenario which HF is going to go forward a little more. Now, if we look at choice A and B, now again, it does speak to Le Chatelier's principle in some aspects here, and that's why this is a little touchy or kind of a question. If I have KF, we should know KF is a salt that breaks apart into K plus and F negative. And there is no potassium, so there's no common ion, but adding more F negative would cause this reaction to go more so in the reverse. Okay, so this would be a scenario where increasing the F negative, this would force the reaction to go more and have more undissociated HF, so that wouldn't work. This is going to dissociate for the same reasons to an H plus and an HSO4 negative, and this would react with water, and this would increase the H3O plus concentration, and that would also force the reverse reaction. Now, if we look at Le Chatelier's principle, I love to use my table, stress and response. If we increase the H plus or the H3O plus, the response bar reaction equilibrium will look to decrease it, and it decreases it by shifting to the other way to lower the both of these guys. And if I was to increase the conjugate base, the reaction would look to lower the conjugate base to regain equilibrium by being more spontaneous in the reverse again. So both of these are not good choices. Now, so we're down to two choices. So it seems the obvious choice would be to increase the molarity of the HF. Okay, so if I increase the concentration of the HF, and I would be doing so by using 10 molar HF, it seems that if I increase the HF, the reaction would look to respond by lowering the HF, okay, and going forward. And in my estimation, that's, of course, something that probably does happen instantaneously, but it happens, but what happens pretty quickly by having that more HF, we're going to produce a lot of HF too, or more HF that's going to ionize with water. So it's what we have to understand here is that the Ka really drives, whatever that Ka is, that really drives how well HF dissociates. By adding more of the acid is not going to drive this reaction to have more undissociated F compared to A. When we mean by percent ionization, if we don't understand that, we know that HF likes to stick together. It's a weak acid, so it barely comes forward naturally without a strong base. So it barely does that. That's why the Ka is very small. The Ka, again, is products over reactants. So if it barely goes forward, you barely have any products. You have little products. That means you have a lot of reactants. Your Ka with the denominator big is very small. Okay? So it barely goes forward. And the Ka is a measure of how well it does so. Having more of these will not make the reaction separate even more percentagely speaking. Meaning for every, let's say for every 10 HF molecules, let's say we produce one F negative because most of them stay unreacted. So if we added more of the HF, yes, we'll have more of these numbers top and bottom, but the ratio would be the same. Maybe now we have 1,000 HF and now only 100 F negatives come off, but that ratio is still the same percentage, 10%. And I'm guessing, I'm sure it's not even 10%, it's like 5%. But you can see that that wouldn't change much, okay? So that would stay the same, and therefore we wouldn't increase the percent ionization. Again, how well HF separates is really dependent upon, okay, temperature, of course, because K is dependent on temperature, but really it's dependent upon how strong the conjugate base can reform the acid. Remember, this sucks up protons and reforms the acid. That's why it is a weak acid. So that's why C isn't the answer. It appears it might be based on, hey, Le Chatelier's principle, but it's because the conjugate base, weak acid, stronger conjugate base, forces the acid back. It's not the best answer. So D is the best answer. And thinking about D, let's make some space here. D is the best answer because if you think about what the Ka is in this case, and the Ka is equal to the products over the reactants, and let's try to do this again. Okay, so if you do this products over reactants business, okay, we have what in the reaction? We have H3O plus times the concentration of F negative over HF. Notice that H2O is not in the expression because it's a liquid. Solids and liquids don't apply. Now, if I was to dilute the water, that means the concentrations all drop. Okay, this would drop and this would drop. And because there's two reactants, okay, you would have a smaller value on top. So your Ka, okay, basically what happens is now it's no longer a Ka once you dilute it. Now we're going to be basically at a Q position. Okay, Q is the reaction quotient. So think with me for a second. Yeah, we dropped the concentration of the reactant the same as the individual products, but because there's two of them multiplied, it's going to have a greater effect. So we have less what? We have less products than we're supposed to. Okay, if we have less products, that means this value, which was a K, is now a reaction quotient, and now Q, and I love to draw this, here's my K, my Q is less than my K. So the reaction goes forward more, and that'll create a scenario, if we're going to go forward more, where we're going to change this ratio. There's going to be more F negatives than HFs than normal, and that would be the best answer. That's a slippery slope question, okay? And that's why D is the answer. By diluting them, you're creating a reaction quotient that is now less than, right? If it was greater than, it'd be over here going backwards. So when Q is less than K, the reaction's going to go forward to increase the products to their ratios that will equal the K. And if we're favoring the forward, there's going to be more dissociation of HF naturally. So again, slippery slope, 33 is D. 34. Okay, number 34. Calcium hydroxide, strong base, precipitates, becomes a solid when a gram of calcium chloride is added to a liter of this, 1 liter of distilled water at room temperature. Okay, so we know that a gram somehow forces the precipitation, okay, but that doesn't tell me that it's exactly a gram does that. Okay, so we dissolved a gram of calcium carbide into water, and that was enough to cause this to precipitate. All right. Now, if 0.064 grams of calcium carbide is added to water instead, and all of it reacts, will it make a precipitate of the calcium carbonate? Now, we don't know if this is the Mason-Dixon line or if this is exactly the amount. So we're going to have to evaluate Q versus K. I do know that a gram dissolved made the reaction precipitate. Now, when you think about precipitation, I'm going to flip this on its head. Calcium hydroxide, okay, is in equilibrium with its ions. And I'm drawing this because I have a KSP given to me. And anytime they give me a KSP, I'm going to draw the reaction this way so I can evaluate the KSP properly. All right, the products for KSP, solubility product, are the ions. So that's why I write it this way, calcium plus 2 and 2 hydroxides. Okay, so what we have here is that the KSP is equal to calcium plus 2 times the hydroxide, and there's 2 of them. Coefficients become exponents, and we don't divide by this because it's a solid. So it's the product of the ions. Because KSP is really talking about the ion product, solubility product, how many free ions you have, I read it this way. Now we know it's equal to 8.0 times 10 to the negative 8. All right, well, now they're giving me a 0.64 gram sample of calcium carbide. Okay, now it's dissolved in a liter, so that's going to give me my easy molarity. So I just got to get moles out of this. They told me for quickness that 64 grams equals 1 mole. So clearly 0.064 grams over the molecular mass is 64. And if I can't see this, okay, it's some ratio of zeros. But if I go from 64 to 0.064, I'm going 1, 2, 3 motions. So this answer is that this is a thousandth. 0.064 compared to 64, I moved over 3 zeros to get there, just so I can see how I did that. 3 zeros is a thousandth, okay, which is the same thing as 0.001, or 1 times 10 to the negative 3. So now, party people, I know that my calcium, I'm sorry, my calcium ion concentration is 1 times 10 negative 3. Now, how do I know that? I found that there's 0.001 moles. This is actually moles, right? And I'm dividing it by the 1 liter to get molarity, and I know, careful, there is 1 calcium per calcium hydroxide formula. So that's why I was able to do this to find my molarity or my concentration. If I was doing it for the hydroxide, I would find my moles 0.001, then I would times by 2, okay, over the 1 liter, because there's 2 hydroxides. You got to look at your stoichiometry, not just get lucky. In this case, it was a 1-to-1. So now, party people, I know the concentration of my calcium. So I'm going to put that in, rewrite that over here, and I know that it's 1 times 10 to the negative 3. Okay, so what must be the concentration of my hydroxide that this reacts with the water? Well, it's got to be stoichiometrically twice that, right? If I know the concentration, so here I have to use my stoichiometry. All right, so it's got to be twice that. So that would be what? So doubling this value would be 2 times 10 to the negative 3. Now, why am I doubling it? Because for every one of these, there's 2 hydroxides. I found the calcium concentration. This has to be twice as much, okay? Because there's 2 here to 1. All right, now don't forget, coefficients become exponents, so this becomes squared. Now, this represents Q. It's a reaction quotient. I know the value of my K. Let's go see what this is. All right, well, we're going to square this. 2 times 2 is 4. And then, of course, 2 times, now when you timesing numbers with exponents, you're adding them. So it becomes 4 times 10 to the negative 6, right? And I'm going to times that by 1 times 10 to the negative 3. And you can see I get 4 times 1 times, now when we multiply, we're adding, times 10 to the negative 9. And that's my Q. What's my K? My K, okay, is 8.0 times 10 to the negative 8. This is 4 times 10 negative 9. So we can see clearly that my Q, okay, is less than my KSP. Now, if that's the case, how many times have I written this? Here's my K. And if Q is, if Q is less than, I think I wrote the wrong symbol. I said it right. Q is less than, okay, my KSP. Q would go here. And therefore, it's going to want to go forward. And when it goes forward, we're going forward in this reaction. We're not going to see, all right, any precipitate. We're going to see free ions. Only when the Q gets equal to K and past do we see some precipitate. So we would say, calcium hydroxide will not precipitate because Q is less than K. All right? And that's all we're doing here is evaluating that. So yeah, it becomes a little tricky in terms of the math, but the math really was, the hardest part was seeing that was 0.001, move the decimal place, and then multiplying numbers with exponents, you're really adding them, okay? So really not a big deal. 34 is D. Number 35. So reaction 2 occurs when excess 6 molar hydrochloric acid is added to 100 milliliters of a sodium hypochlorite of an unknown concentration. If the reaction goes to completion, that means that the forward reaction has been driven completely until we ran out of at least one of the reactants, the limiting reagent. And they didn't really need to say that because they had excess hydrochloric acid. So in any case, if the reaction goes completely forward, okay, and we produce a product, in this case it's chlorine, and we know we produce 0.010 moles of it, okay, what's the molarity of the original solution? Well, the original solution is in 100 milliliters, and we know that molarity is equal to moles over liter, and we know that the original solution is in liters, has to be 0.100 liters. I just converted my 100 milliliters to liters. That should have been easy. All I need to know is what the moles of my original reactant is. Now let's go to the reaction if you don't see what I'm talking about, and that's reaction 2. So we go up, 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 and we see reaction 2 here. And we look at reaction 2, we see our chlorine as our product, and we see our sodium hypochlorite as our reactant. And this is a stoichiometry problem. And it's a very simple one because there's a 1 in front. There's no number in front, so it implies a 1. No number in front here, so it implies a 1. So as many moles of chlorine that I make is as many moles of sodium hypochlorite I started with. So that's pretty simple stuff. Going back to where I was working, I can see that if I produced 0.01 moles of chlorine, then I must have started with 0.010 moles of my compound. So what's my math here? Now, some people don't like this math, okay, because they say I need a calculator for everything, but you can do this. If you're dividing a number by a number smaller than 1, this top number has to get bigger, right? And if I divide by a number that's bigger than 1, just like a 2 or a 3, I'm cutting this into seconds or thirds. It's getting smaller. So if you think of some basic math, this number is less than 1, so this top number is going to increase. Now this number is 0.1, which is a tenth, which means this is going to increase 10 times. If I divide by the number 2, I would have the top number. If I divide by 0.1, I'm going to increase this by 10 times. All right, so this becomes very simply a molarity, moles over liter, to be 0.10 molar. And that is choice, okay, C. Right, very simple. Okay, it was in simple. The stoichiometry was a 1-to-1. So if I had the moles of my products, I know exactly the moles of my reactants. I took that moles and I divided it by the liters of my initial solution. Okay, and I just did my very simple math. Again, If the number is bigger than 1, like a 2, like 0.010, I'd be dividing this in half and become what's half of that? 0.005. That number would get smaller. But if I divide by a number less than 1, like 0.1, it would increase it, okay, in this case, 10 times. So choice 35 is C. Okay, number 36. When the reaction 3 occurs, does the hybridization of carbon change? Well, we have C2H2, and if you do the Lewis dot diagram, you'll see that it's C2H2 looks like this, and it's linear. And if you were to count the areas of electrons around the individual carbons, you will see that you'd have to have what we call sp hybridization. Well, why? Because you have this carbon has an S and a P that comes together, and the other carbon has an S and a P that comes together. They're overlapping here is a sigma bond. It's the first bond. And if it's linear, okay, it's because it tells you it's sp hybridization. Here's an oxygen with one valence, and here's another oxygen with another. And then, of course, you'd have the valence of the here. Now, where's the other bonds? Well, if it's sp hybridization, an S and a P came together, and we know that there's 3 p orbitals. They're unhybridized, so they would unhybridize up top and probably front and back, and that's where your pi bonds, or the second bond, would occur. So we would have, if you look at the valence electrons of the carbon, you'd have the 1, 2, 3, and do 4, and this other one would be 1, 2, 3. I'll make this 4, and then we'll do the pi bonds in pink, whatever. So this would be, and let's just change where that last dot would go. A couple dots there. Okay, let's go make that. So we have the 1 valence here. Here's the second valence. Here's the third, and here's the 4th. Okay, now let's do it with orange, because hey, so we have our pi bond here. That's the second bond, top and bottom, or basically this is one orbital overlapping another, unhybridized. And then we have the what? The back and the front, and that's the second pi bond. All right. Bottom line is, when I count for hybridization, I'm looking at the hybrid orbitals and the shape. The shape was linear, okay, and that gave it away that it was sp. All right, and in order to have 2 extra bonds, you have to have 2 unhybridized. So that means sp was the also telling you there. So it changes from sp to something, and now we have C2H2Cl2. And then these are planar molecules, and this is going to look like you have what? You have an H, another Cl, another C. So there's 2 C's. Here's an H, and another Cl. I don't know if it's trans or cis, it doesn't matter. But what you have is you have what? 3 places where there's electrons. And if there's 3 places where there's electrons, that means an S and a 2 P's came together, sp2. Okay? There's no lone pairs, so you would just count those 3 areas. Notice it's trigonal planar. This would be 1, 2, and 3 as well. So you're going from sp to sp2, and that's why 36 is A. Number 37. Well, number 37, another acid-base question. You can't get away from it. So they're giving you the Kas of the acid. We can see that this is the weaker acid. This is the stronger acid because this has a lower Ka, lower dissociation constant, lower amount of ions given off. Any case, are given in the table above. Which of the following mixtures is a buffer? With a pH of approximately 3. Well, what have I been teaching you? Well, a buffer, a max buffer, is when the pH equals the pKa. And of course it's max buffer because for the millionth and one time I'll have equal concentrations of the conjugate acid, conjugate base and the conjugate acid, and this whole expression will go to 1. Log of 1 is 0, and you're left with the pH equals the pKa. So they want to have a buffer of about 3. So I'm looking for a pKa that's about 3. And if you were to plot, okay, a titration curve, you would be looking at the buffer region, max buffer position, halfway from equivalence, equal a 3. That's what we want. So clearly, now I don't advise you try to do this in your head or on paper, but take the negative log of this, right? The Ka, little p means negative log, so take the negative log of this. You can make this equal to about 1, okay? 8.3 is getting close, but this would give you approximately, what, 4 or 3, and this is about the same reasoning. If I go 1 times 10 to the negative 10, make this a 1, this would, when I do negative log, this would give me a pKa of about 11. So you say, well, where's the 3? Well, the closest one is this one. So we know that this is the one we want. Okay, in truth, 8.3 times 10 to the negative 4 is coming close to a 3. Okay, and again, estimate 1 times 10 to the negative 4. You should be able to do this, party people. 1 times 10 to the negative 4, negative log of this means take the positive value of that exponent. That would be a 4. And since it's 8.3 times 10 to the negative 4, that actually is coming close to 3. But if you don't see that, this is the closest number. So this is the chemical that I need. But to make a buffer, I need its conjugate acid, and I need its conjugate base. Now, notice they're adding base here. So notice what we're going to do here. If you want the max buffer position, you want to halfway titrate. So look what they're doing. First of all, the CH3, NH3 plus I'm getting rid of. Okay? And so anything with the CH3, NH3 I'm not even considering because that's not going to give me the buffer I need. All right? It's going to be a buffer, okay, of 11. I want this one that's close to 3. So it's going to be between B and C. Okay? Now, if I have a 100 milliliter mixture of a 0.1 molar conjugate acid that I need, and I'm going to add 50 milliliters of a 0.1 molar, okay, notice they're the same concentration, but half as much, that's going to half titrate me to that max buffer position, and that's why B is the answer. Now C, okay, says I take NaC3H5O3, that would be the conjugate base, okay, and then add 100 milliliters of more base. If you notice, I wouldn't have any conjugate acid. So one of the ways that we create a buffer is half titrating, and that's what B is, get to the halfway point, or adding conjugate acid and conjugate base with a salt. However, in this case, if they didn't give us conjugate acid, this is conjugate base and more base, so there's no acid in our mixture. That's why B is the answer, okay? B, because we're dealing with the conjugate acid base pair of the pKa of the acid, which is closest to the 3, which was this one. Okay, so 38 is B, 37 is B, 38. All right, number 38. We're basically looking at these two molecules, and we're trying to understand which would be the stronger acid. So understand this dotted line here is a pair of electrons. And essentially, the stronger the acid, the more that these pair of electrons will drift toward the chemical. Now, you can see 3 of these electronegative elements, these 3 oxygens, and chlorine contributes as well, okay, although it's positively charged in this case, but it doesn't matter, it's the same idea, it's going to draw in electrons, is going to draw in these electrons in closer. I like to call them electron drift. So because this has an additional oxygen, there's going to be more drift and these electrons pulled this way. Now, if you look at your choices, none of that is explained. Another way to talk about how well this electrons can be pulled in effectively and allow the what? The H plus to leave is to talk about the stability of the compound once the H plus leaves. Now, how well can it pull these over is the same way of saying how stable can it exist without the H, okay? So what adds to the stability is these 3 electronegative atoms. Also, what also adds to stability, if you can have delocalized electrons in this case, and in this case, both of these get stabilized because there is resonance that could help stabilize the structure. So stability is another word for how well the conjugate base can exist without the H plus, which is the same thing as saying how well can it pull in the electrons and exist with it. So stability, okay, is an important word here that describes how well these electrons can drift and be pulled in and exist that way, which means that proton can be ejected. So the best answer is that this one with the extra oxygens does the trick, creates the most stable. So HCl3 is a strong acid because the additional electronegative atom on the chloride stabilizes what's remaining, called the conjugate base. Okay, the HClO2 is not the winner because it has the least amount of oxygen. And by the way, the chlorine's not as positive here as well. Okay, so B is the best answer. London dispersion forces between the elements has nothing to do with how well these electrons can be drifted away and thus increase the stability. So 38 is B. 39. Okay, number 39. If equal masses of the following compounds undergo complete combustion, that means they react with oxygen, whatever the hydrocarbon is, and they produce CO2 and water, which will yield the greatest amount of CO2. Now, as we talked about previously in another question, all the carbon comes from the hydrocarbon you start with. So if equal masses of these organic molecules that have carbon, hydrogen, and some oxygen, they want to know what's going to produce the greatest amount of CO2. Well, the greatest mass of CO2 means who has the greatest amount of carbon? But wait a minute, they all have equal masses. So really the question is, who has the highest percent of carbon? Okay, now you may say, oh, right away, okay, well the smallest one will have the greatest amount of carbon, but we're talking about percent by mass. Okay, if you notice, this is a 1 to carbon ratio. So this is a 1 to 4 ratio of carbons. So some of its mass is due to 4 carbons. Look at benzene. Benzene is a 1 to 1 relationship. That means it has the least amount of mass due to its entire mass because it's a 1 to 1 relationship. So if you look, you think methane might be the answer because it's the lightest molecule. It's got the poorest what? Relationship in terms of how many hydrogens to carbon. So benzene's the answer because it's going to have the greatest percent by mass of carbon. For the same amount of grams of each of these, okay, you will produce more mass of carbon. You say, Mr. Grotsky, benzene's heavier, so you're going to have less of it. There's going to be more methanes. But guess what? There are 6 of these per 1H, and there is 1 to 4. So when you break it down, yes, benzene is heavier, but when you look at its in total mass, there's 6 carbons per 1H in its mass. There is 1 carbon for 4 H's. So in the same mass, there might be more moles of methane, yes, but there's actually more moles of carbon per hydrogen in the benzene. Okay, if you look at B, it's a 1 to 2 ratio, and for glucose, it's a 1 to 2 to another 1 here, so that oxygen adds mass to it, so it's kind of like having a 1 to 3 ratio of other things. So the one with the greatest amount of carbon, okay, or the highest percent by mass of carbon is the one that will produce the greatest amount of CO2. Choice 39 is A. 40. So in number 40, we've got a reaction at equilibrium. We've got our delta H that's positive, and the reaction is represented above is at equilibrium, which the following will decrease the amount of calcium oxide in the system. So we're looking to decrease the calcium oxide. So we're looking to make the reverse reaction what? More spontaneous. We want to, or we could say we want to shift the reaction to the left. Now, I always teach to make things simple, a little graph, a little chart. Stress response. Okay, so if I increase the volume of the reaction vessel at constant temperature, by increasing the volume at constant temperature, I'm decreasing the pressure. So that's really my stress here. Decreasing the pressure is the stress. Reactions are going to always respond by moving back toward equilibrium to regain balance. As I've always keep writing, equilibrium K, reactions always go toward equilibrium. So by lowering the pressure, we've basically unbalanced this out of equilibrium. And now the reaction is going to respond and shift by increasing the pressure. And if you remember, only things that are really affected by pressure are gases. So we have one gas on this side and we have 0 gases on this side. So to increase the pressure, I'd have to shift toward the side to make more moles of gas, and that's not going to increase my calcium sulfide. Not sure why I had an arrow down. I want to increase my calcium sulfide. So by shifting this way, what happens is I would definitely decrease it. So I definitely want to shift this way. Okay? Now, and I want to increase the calcium sulfide scenario. This is what I want. What would happen, of course, is that shifting this way, I would use it up and make more of these guys. So that's not a correct example we want to do here. Okay, B, lowering the temperature of the system. Okay, what would that do? Okay, well, notice where the heat is, and I have to consider where the heat is here. Because it's positive, it's endothermic, and that heat or energy goes on the reactant side. So if I lower the temperature, the reaction is going to shift to increase the temperature. Okay, if that's the case, I'm always going to favor the what? Okay, I'm going to favor the exothermic way. So if I decrease the temperature, the reaction responds by increasing the temperature, and it basically will make a more spontaneous pathway to the left, as Beyonce would say, and therefore we would make more of these guys and use up the reactants, and that is your answer. Okay, that's why I circled it. Okay, now understand, in truth, we're not shifting out of equilibrium. Once we start messing with temperature, what's happening is the equilibrium constant is changing. In fact, what happens is, in truth, this equilibrium constant is moving this way. It's getting smaller. And as it gets smaller, okay, what was once okay to be at equilibrium now moves in this fashion in reverse to get back to it. So the equilibrium expression actually dropped and we found a new position, which is now over here, and these things moved in this direction to regain its balance, so to speak. Now, if you go back to the other ways, wrong ways, removing some CO2. So if I decrease CO2, the reaction is going to shift to make more CO2, and it would have to shift and be more spontaneous in this way to make more CO2. Okay, and that, of course, is incorrect. And removing some calcium carbonate would have no effect because K is dependent upon concentrations of gases, okay, not solids. Equilibrium is based on the concentration of the products over the reactants, and solids and liquids do not apply, so there'd be no effect for D. 40 is B. Number 41. Okay, number 41. What we have here is we have 4 different acids, okay, concentrations, I guess, and they want to figure out, to maximize the yield of a certain manufacturing process, a solution of a weak monoprotic, that's 1H plus acid, has a concentration between 0.2 and 0.3 is required. So they want to make sure that we have a concentration between 0.2 to 0.3 molar scenario for my acid. Okay, so we have 400 milliliter samples of the acid at different concentrations. So we don't know which one is. So one of these 4 has a concentration of the acid to be between 0.2 and 0.3 molar. Okay, and we're going to use 0.2 molar NaOH. Okay, the volume needed to reach the equivalence point, which is when the the endpoint or the equivalence point, which really means where the H pluses equal the hydroxides, is given. So this is the volume needed to get to that equivalence point. So basically, by knowing the base solution, which is 0.2, they want to know which acid solution is approximately between 0.2 and 0.3. All right. Now we can calculate this. All right. So how do we do this? Well, here's what I know. If I have 0.20 molar acid and I have 100 milliliters of the, let's put it this way, if I have 0.2 molar base, okay, and this is my base, and I have 100 milliliters of my acid, okay, so my acid is going to have 100 milliliters, and I want to at least know if it's between 0.2 and 0.3. You probably can see that. Let's go figure out how many milliliters we need for 0.2. If my acid is 0.2, now the range is 0.2 to 0.3, but let's pretend it's 0.2. If my acid is 0.20 molar, okay, and I have 100 milliliters of it, can you figure out how much base I'm going to need to reach the endpoint? I hope you can see this. If the base is 0.20 molar, and I'm going to pick the 0.2 molar, the first part of the range, if they're going to be the same, then can't you see, as the song goes, all right, that I'm going to need 100 milliliters of my base? Now, there's nothing here with 100 milliliters, but the closest one is 115. Okay, so if you wanted to use MV equals MV, and I'm not a big fan of that, okay, you can clearly see that the moles of the acid equal the moles of the base. 0.2 times 0.1, if you make that in volume, would give me the moles, and the moles of the base equal the moles of the acid. So because I said 0.2 to 0.3, it has to be a little bit bigger than 100, and the one that's a little bit bigger than 100 is 115. So that's why C is the answer. Really, you're just estimating here, and that's an estimation question. So C is the answer. I would not ask you or spend the time to come up with the exact amount. You don't have to. This 200 is so far away from the 115, easy to estimate. 41 is C. Okay, number 42. Which of the following rate laws for the overall reaction corresponds to the proposed mechanism? The mechanism is the series of individual elementary steps that makes the overall. Now, they told us that the slowest step is the first step. So this is the rate determining step. So this is where the rate law comes from. So rate law is equal to R times K times, well, if we have a slow step, the rate law comes from this step. And since this is an individual elementary step, the coefficients become the rate orders. So I have got CL, because it's a coefficient of 1 or nothing, 1 is implied, it's a 1, and I've got this to the O3 to the 1. Very simple, and that's why B is the answer. All right? You cannot look at an overall reaction and do this. It would be a mistake to go R equals K, O3, because that's my reactant, and put a 2 here. That's a big no-no, and they have that as a distractor. Why is that a big no-no? Because, my friends, in chemistry, that you cannot look at the overall and use the coefficients. You have to look and understand through experimentation what the orders are, or if you know through experimentation what the slowest step is, that this is now an elementary step, and the coefficients equal the exponents if it's a single step. You can't look at the overall and know that. But inside a mechanism, these are the individual steps, so the coefficients work here. Now, I'm not a big fan of this problem, because what they have here is they have something called a catalyst. The catalyst started this series of steps here. Without this catalyst, you wouldn't have these two steps. So we're seeing that the catalyst is part of the reaction rate law. And oftentimes you'll see it without. But again, it's what we have to work with here. And so the best answer is choice B. Number 43. So number 43, which of the following reaction energy profiles best corresponds to the proposed mechanism? Well, we know the mechanism was 2 steps. And because the catalyst created a whole series of steps that were different from the original, we should see that by the potential energy changes. So if we go back to our diagram that shows us, okay, we see 2 steps. They gave me the delta H of the reaction to be negative, so it's exothermic. Okay, so going back to where I was, I'm going to pick an exothermic choice. A and B look good, they're going down. And then C is a possibility. D is definitely not, okay, because we're endothermic. We're starting low and going high. Delta H would be positive because you're going up here. So that's not a great example. Okay, now C, okay, shows me being exothermic and then endothermic and overall, okay. That's, I guess, could be a possibility, but I think the best thing here is to understand is that we have the best way to think about this is if this was the potential energy curve. Sometimes it'll be shown like that, and sometimes without the catalyst it would look higher and then come down. These individual steps lower the overall cost to start the reaction. B is the best answer because you can see that going high to low, it's an overall exothermic. So thinking about why B is the best answer, notice this doesn't take into consideration the 2 individual steps that occurred, the 2 reactions, so I'm getting rid of A. So B and C are now at the forefront of my discussion. And what I'm trying to draw on B is that oftentimes you'll see potential energy curves look like this. Okay, that's for the overall reaction. Now, if you add a catalyst, we know the activation energy from where you start to this peak energy barrier that you have to overcome to start the reaction. We know that a catalyst lowers that value, and it does so because it starts a whole series of reactions that collectively are lower in energy cost than without the steps. And you see these 2 little humps here, the 2 individual steps. So the catalyst creates that scenario. And that's what I was trying to deal with there, so that wasn't really very helpful, I guess. But the reason why C is not going to be the correct answer, although we're seeing 2 steps, we're seeing an exothermic step, and then we're seeing an endothermic step. So my guess here is the poorest answer is because we know the second step in our rate law is going to be the fastest step, correct? If we go back to our reaction, okay, the second step is the fastest step. Now, fast steps occur because what? Activation energies are lower. And in a case of C, we've got a what? A bigger activation energy than we do with the first step. The first step was slow. So it would make sense that this is the best answer. Let me clean this up because it makes sense that this would be the best answer because the slowest step, okay, would have the largest activation energy, and the fast step would have the smallest activation energy, or E of A, okay, right here. Whereas in this example, we have the larger E of A on the second step, and that is just not consistent with the mechanism. If it's the second's going to be fast, you can't have a faster step with a larger activation. As activation energies drop or get smaller, the reaction goes faster. Less energy is needed, okay, to overcome the activation energy for the same temperature. So that's the reason why B is the best answer. We have the slowest step having the greater activation energy, and the second step in the process have the smaller. So that's why B is the answer. Really nice little question. 43 is B. 44. Number 44 looks like a more difficult question than it really is. The proposed mechanism, it's the same mechanism that we had in the other page in a more general form. Okay, this was Cl, but now they're writing X. Okay, species other than Cl can also decompose O3. O3 decomposing, that's the overall, and these are the 2 steps. Which of the following chemical species most likely decompose O3 in the upper atmosphere through the mechanism? Well, we knew that chlorine did the job, so who else is what? Most similar than chlorine, right? This is just a fancy way of hiding a very easy question. Who's the most similar than chlorine? Well, as you learned, who is in the same family group? So here's chlorine, it's in the halogens. We have fluorine, chlorine, bromide, iodine. Who else would do the job? Well, we would say bromide because it is in the same family of elements. It has all the same valence electron, right? If you have the same valence electrons, you have the same what? Chemical properties. Okay, yes, bromide is a little bit bigger, but still would work nonetheless, and that's the reason why bromide. So all that was a simple answer is, can you identify the element most similar to chlorine? And of course, it'd be in the same family of elements because of the same chemical properties due to the same number of valence electrons. So 44 was B. Number 45. Okay. The wording here is a little bit confusing if you're not used to it, so I really would suggest you just look at the reaction. But a solution of a salt of a weak acid HY. So the salt of a weak acid, well, acids plus bases equals salt and water, but if you have a salt of the weak acid HY, my understanding of that would mean that you had like sodium, whatever the conjugate base is, Y, and you add that to water, it breaks apart into Na plus and Y negative. Now, if this was from a weak acid, and this is its conjugate base, Y negative in water, okay, would be able to yank an H plus from it because a weak acid strong conjugate base, as I've been explaining, would reform the acid HY. Okay, yes, not all of them would because it's still a weak base, so you would produce two scenarios. Both things would be added. So by adding this to a solution of already a weak acid, you'd produce these two scenarios by how I explained that there. But if you don't like that, just look at the reaction. Okay, based on the information given above, which of the following species is the strongest base? So is this the strongest base or is this the strongest base? That's not a base. That's not a base, right? Okay, conjugate bases have the ability to absorb protons. These guys are proton donors, right? HX going to H negative means they've donated the proton either to water or maybe this Y. So these are acids. This is the base. This is the acid. This is the base. So if you picked A or C, you don't have a good understanding of what a conjugate acid is. You're a proton donor. How did HX become X negative? Because it donated a proton. Okay? And so how did Y negative become HY? Because it accepted. And bases accept protons, acids donate. Now, the key to the question to know which of the following bases, okay, Y negative or X negative, is the strongest conjugate base is by looking at the equilibrium constant. The K is greater than 1. What does that mean? Well, KQ is equal to the what? As I've been talking about all day. Products over reactants. So generally speaking, you've got more products than you do reactants. That means there's an overall, we would say that it's more spontaneous in the forward direction. There's a shift, if you want to say it that way, but generally speaking, there are more products, which means the reaction likes to go forward more than it likes to go backwards more. And if you say that, why? Exactly, because Y negative likes to what? Reproduce the acid better than X negative reproduces the acid over here. So this Y negative has a better ability to pull protons either from water or the HX than does the X negative pulling protons from the water or HY. So the idea here is that who is the better base? We would say Y negative is the better base, and then hence the answer, because it's able to create what? HY by absorbing protons better than X negative is able to hook up to and pull protons and reform HX. How do I know? There are more what? Products favored. Why are there more products favored? Because K is greater than 1. So there's a lot more HY and undissociated H negative than there is HX and Y negative. Why? Exactly, because Y negative has a better ability to force the reaction to go forward. If X negative was a stronger base, okay, it would pull H's from, let's say, HY or water and reform HX, and there would be less products, and less products would mean a K is less than 1, and we would be going the opposite way. So 45 is B. 46. Another question about equilibrium. How many equilibrium problems have we seen, acid, base, or not? It just continues that they want you to understand these relationships. So listen, I've got a Kc. Now, what does that mean? It just means that I've got an equilibrium constant using concentrations, not partial pressure. So it doesn't matter if it's Kc or Kp, or if it's Keq or Ka or Kb or Kw. It doesn't matter. They're all the same. Now, this is a big number. So who is favored? So the Kc is huge number. So we know that, generally speaking, the reaction is more spontaneous in the forward direction. There's a lot more products, and equilibrium position favored than reactants. A heck of a lot more. There's very little of these reactants. So when you look at a mole sample of X and a mole sample of Q are introduced to, again, previously evacuated rigid container and allowed to reach equilibrium at a certain temperature, according to the equation, at equilibrium, which of the following is true about the concentrations of gases? Well, we look at A, R is equal to 1/2 Q. Well, R stoichiometrically, yes, is 1/2 of what, so this will be a plus 1/2 of whatever Q loses, no question about that. But at equilibrium, they will not equal these values because the reaction is almost at completion. When a completion means we're almost driving, this is an E completion, we're almost driving the reaction completely forward where there isn't any reactants. So it's not going to be a 1/2 relationship, okay? So it's good. As it goes to completion, it could get close to that, but it won't be perfect because there'll be some reactants there. So A cannot be correct, okay? So that is, now B, there's another stoichiometric relationship, but I don't think that's even correct. Q relates to X how? Well, we know stoichiometrically it's a 1:2, but did we add equal amounts and there's excess here? Okay, so we could do a limiting reagent to see how much it would be there, but it still doesn't matter whether there'll be half X or not. This reaction is going to completion. Okay, now yes, if you think about it, if it's a 1:2 relationship, all right, we know that 1 mole of Q would be probably entirely used up if it went to completion. It's not completely at completion, right? It's going to go almost to completion. I should make that case. So if I had a mole of this, okay, and we would need 0.5 moles of this to go forward, so almost all the Q would be driven off. If they're not seeing what I'm doing here, I'm doing a little limiting reagent. Here's my X and here's my Q, okay, in my reaction. And if I'm adding a mole of each, okay, this being twice as much Q gets used in the reaction, then I'm going to use all of 1. I won't use all of the X's 1. It'll be 0.5. Now again, I guess the best way for me to do that would be something like this. Start at a mole of each, and this is going to use all of it, -1. This will be minus 0.5 because of the stoichiometry, and then when you do at the end, this will be a 0 and this will be 0.5. So clearly there's going to be a lot more X, and Q won't equal half of X. It will if it was totally at completion, but it's not quite, okay? So that can't be the answer. All right, now D makes no sense. No way X, Q, and R and Z all equal each other at equilibrium. You have no idea what's going on if you pick that choice. In fact, I'm just going to eradicate that. They can't ever be equal. Okay, only in some weird condition will these be equal. Maybe at a Q if you add them. So I'm just going to take that away. That's the worst answer. Sorry if you chose that. Now, this has to be by, how can I say, process of elimination. That has to be your answer because, let's see, R is equal to some Z, okay, which is going to be greater than Q. Well, obviously the reaction's going forward mostly, so Q is the smallest. That part makes sense. Why would R and Z be equal to each other? Because stoichiometrically, for every two Q's and one X, one R and one Z is made. So that's why C is the best answer, okay? These would make more sense if it went totally to completion, but it didn't, okay? It didn't. It's favoring the products, but not completely. This would have to go approaching infinity. It's big, okay, but there's still some of these here, so these aren't completely right. This is the best answer. 46 is C. Okay, number 47, we've got this really potential energy and internuclear distance graph that pops up all the time. It's part of the curriculum. Have to learn it. What you have to understand is we have two free atoms out here, atom A and atom, let's say, B, okay? And they're nowhere near each other, and they have some potential energy. And it's pretty high considering that when they do bond, they're going to achieve some kind of electron configuration that is more stable. Being stable means you are low energy. So they're going to achieve some kind of stability when they bond. So as they get closer together, okay, the potential energy drops, okay, until they reach the maximum potential energy. So there's an attractive force between the protons of the two reactions, and they are attracting the electrons in between, and that simultaneous attraction creates a bond. So as they get pushed closer together, they become more stable. The potential energy drops until they find the maximum position. Now, this is this part of the graph, due to the attractions that the nuclei have for electrons. But as they get closer and the distance becomes smaller as I move this way, if I push these protons or the protons in a nucleus of two atoms too close, then there starts to become some repulsive forces due to the protons being too close, and the potential energy becomes increasingly higher and becoming more unstable. Remember that unstable guy in the city? You don't want to look at him or do anything because he might do something. He's got high energy. So the energy drops as they get closer because the nuclei of each of these atoms can start attracting these electrons. But when they get too close, these protons in the two nuclei, if the internuclear distance gets too close, start repelling themselves. So we have essentially attractive forces here, okay, in this area, to electrons, and then we have repulsive forces in this region here due to the nuclei getting too close. So the best answer is A, the attractive and repulsive forces are balanced, okay? So looking at the question, which of the following is true regarding the forces when the atoms in their internuclear distance is X? And X, as I've overwritten it here, overwrote it, okay, is the lowest position. And that we must have a balance between attracting electrons and repelling of the protons between the nuclei. So the attracting repulsive forces are balanced so that the atoms will maintain an average internuclear distance. Now, I will say this, they don't stay here, okay? They could absorb some energy and vibrate either this way or this way, and that's the infrared motion or the infrared spectrum of elements is how well their bond distances actually can change when they do some symmetrical or asymmetrical stretches. Okay, so the vibration energy of atoms is how much they go up and go down, and if they go up, they're going to lose energy and emit the energy as infrared going down. So the vibrational or movement around the bond energies is what causes the infrared spectrum or absorption or emission or absorption of atoms moving up and down this position. So 47, the best answer is A. Okay, 48. So in this reaction 48, they give you a reaction, and then in order to determine the order of the reaction, we have some data. Okay. Any case, they're not asking for you what the order is. If you would, you could eyeball this and figure that out. But look at the question. In trial 2, which of the reactants would be consumed more rapidly? Why? So we have reactants being consumed to make products. Well, whether it's trial 2, 1, or 3, look at the stoichiometric coefficients here. There's 1 to 2. So the rate of formation of this guy is equal to twice the disappearance of Y, or 1 time the appearance of X. I'll say that again. Look at the stoichiometric coefficients. The rate of formation of your product is equal to exactly the rate of disappearance of X, but the rate of disappearance of XY is what? Twice the rate of disappearance of Y because of the 2. So you're going to lose Y twice as much as you lose X because you need 2 of them to come together. So you don't really have to deal with any of this, but look at the stoichiometry. In trial 2 or trial 1 or trial 3, which reactants would be consumed more often? Why? Well, it'd be Y because the rate of disappearance will be double that of X. Well, why? Exactly. Okay, because of that 2 right there. So a lot of information. You could spend a lot of time reading this to understand it. It really is really helpful to go to the question first to see if this information is even helpful. Okay, certainly I could use this for another different 5 or 6 different types of questions, but the all understanding is that because of the 2 there, you're going to lose Y twice as often as you lose X to form XY2. So 48, okay, is just D. Duh. Okay, now 49. In 49, we've got paper chromatography, okay, and we're separating a mixture based on their different types of solubility. And normally speaking, the paper is normally going to be a polar cellulose, or it could be a silicon substance that's also polar, depending upon the plating or the plate. And we have the hexane, which we should realize is very nonpolar. So they say the sample has a pigment separated into 2 components, X and Y, so it's a mixture. X and Y will have different solubilities. They may be similar, but they all have their individual solubilities. The surface of the paper is moderately polar, so they're telling us that. What can be concluded about XY? Well, if the component X traveled by capillary action up into the higher portion, that means it didn't stick to the paper as well. And since the paper we said was polar, that would mean that the component X preferred to move with the nonpolar hexane. So this was more nonpolar. And because component Y in the mixture didn't move as much, it preferred the polar mixture. So component Y had less nonpolarity, or it was more polar since it preferred to stick with the paper. So we could say that Y, okay, is more polar than X, okay, which would be choice D, okay, and let's see if I could see those choices again. So yeah, so Y is more polar than X, choice D. Why? Again, because it stuck, it moved the least amount on the paper, which means it preferred the polar, which means it had more polar characteristics. And X moved more with the nonpolar solvent, which is called the mobile phase, and therefore it preferred, given the choice, to go more so with the nonpolar solvent, which tells me that component X was a little more nonpolar. Okay, so a little nice question about the technique of understanding how chromatography works. But I think even if you didn't, you could have worked your way through that. Okay, so number 49 is choice D. Number 50. Okay, number 50 gives us a spectrum of different regions: ultraviolet and visible, infrared, microwave. And as we should know, very important, the wavelength gets longer as we go to the left, to the right, and it gets shorter as we go to the left. That's why the arrow is going that way. So we should know the longer the wavelength, the lower the energy. Energy is equal to Planck's constant times the frequency. Now, the speed of light is equal to the wavelength in meters times the frequency. And now what we should know is higher the wavelength, it's an inverse relationship, lower the frequency. So either way, lower the frequency, lower the energy. So we know all of this. As the wavelength gets bigger, the energy is dropping. So over here, the energy is lowered. And over here, the energy is higher. Shorter the wavelength, higher the frequency, higher the energy. You should know that ultraviolet burns the skin. Radio waves do not, so higher energy. Now, higher the energy, the more things that can happen within molecules. First and foremost, okay, to move an electron from its stable, let's say, shell to an unstable shell requires the most energy here of all these things. So region X has the highest energy, and we should know that we see colors, okay, in the visible or ultraviolet region because electrons are what? Jumping back to their stable state once they have the exact amount of energy to get to a higher position. Okay, and they go from their ground state to their excited state. So electron transitions of electrons that give us the visible region or the ultraviolet as photons when electrons jump back, okay, is something we should know as electronic transitions. So region X to jump out as B and D. Now, as I've talked about previously, infrared regions is when bonds in atoms like water, okay, rotate, or I should say rotate, they stretch or they move about their bond lengths. So this guy could be stretching back and this guy could be stretching out. So these bond lengths can be changing. So as I talked about in that internuclear distance, okay, graph, that X position here is where the atoms are the most stable, but these bond lengths and bonds can change their lengths depending upon the infrared spectrum. So infrared is about the vibration energy or the vibrating of atoms through their bonds. So we would talk about electronic transition, okay, and then molecular vibration. That's where the infrared region, and that's of course how the greenhouse gases work. Greenhouse gases work by trapping thermal energy by infrared radiation reflecting off the earth, hitting, let's say, a greenhouse gas like water, making their bonds move, okay? And if it moves in either way, it makes them more unstable, higher energy. And then to get stable, they do what? They return back to their position. They go back, right? And they emit infrared. And sometimes that infrared is emitted back to the earth and it maintains the heat. Okay, so that's why looking at transition and vibration, D is the best answer. And of course, the lower energy just can make the molecules rotate, which is a lot less energy needed to vibrate the bonds and or move electrons. That's why D is the answer. 50 is D.